Well, I'd like to start today out by our appreciations for the wonderful speakers and participants and all the interaction we got yesterday. We're getting great feedback. Understand that the exercises for some people are really a positive experience and for others not so much. So, but we're using those exercises really to help us shape what a research plan might look like, what are the major questions, and getting a broad perspective on the policy issues as well. So it's extremely useful for us and hopefully for you ultimately as you look at where you want to play, what research you want to be involved with, and who you want to partner with. So there's a method in the madness, but on the same time, if you are uncomfortable participating in the exercise, please take a coffee break. Don't participate, it's fine. And so everything's optional here. But the plan is really to get a community together to further the research and potentially the exploration for geological hydrogen. With that said, you know, we started out with a foundation yesterday. Okay, the USGS gave us great examples of a methodology they're developing. It's the first of its kind. It mirrors to some degree oil and gas methodology that's well established, but in other ways it's very different. We had then talked a lot about the source rocks. You know, ultimately, without the source rocks, there's no resource. And there were great talks about the various ways that hydrogen can form, the uncertainties. We learned a lot about the uncertainties about the rate of formation, which is going to be a critical question. So we really, I thought, got a great talks on that. And then we went into the Alaska geology, you know, and it reminded me a bit of the Wizard of Oz, where Dorothy's house falls in, and she says, I think we're not in Kansas anymore. Well, we did learn about Kansas, but we also learned Alaska is not Kansas. So it was kind of fun to see just the variation in geology, the tectonics, the structure, the history, and of course the role that oceanic crust plays in this structure is going to be unique to area, you know. But we also saw that the akin to the Franciscan rocks in California. So again, as we as geologists know, the stable craton is very different than the West Coast, and that really got emphasized in that the research that we need to do in geological hydrogen needs to be in many different tectonic settings, because it's going to be there in different tectonic settings, many different geological settings. So that's kind of exciting. So again, if you look at Alaska, we're going to focus on a very different type of geology than we're looking at in the Mid-Continental Rift or in the Atlantic margin. So really fun that we're going to need a real strong collaboration on all these issues together to work those common issues, but then have the detailed work to understand the different geological settings. So really useful base talks. Now we're moving up to we've created the hydrogen. Now, where's it going? The migration pathways, its preservation, and how do we trap it? And there were a lot of good questions on that yesterday, but we focused this again. The foundation is the source, and now we're moving up the ladder to the later parts. And then ultimately, we start introducing the resource management issues and challenges and opportunities by very experienced resource managers talking about, and senior officials talking about their vision of that. And that will continue tomorrow. More on terms of, we'll get more policy. We built the geological foundation now. Now we're going to look at the policy pieces. So that's our kind of our structure. And so we really look forward to today's speakers. And with that, Barb will kind of go through the procedural stuff. Again, if you want to participate, do. If you don't, that's okay too. But in all cases, we get information from you that's valuable. And hopefully, again, this information will be valuable to you as well.
Good morning, Alaska. That's better. Okay, one note for speakers, just for speakers. There is now a pointer here. You can stretch it out and you can walk over to the screen and point at things. We're not using the laser pointer for health reasons. So that'll be up here. Actually, I'll lay it over here. Lots of announcements. We did read through every one of the feedback forms. Thank you, anyone who responded. I want to just reply to some of them. One is, if you can't see, feel free to pick up your chair and move up to the front, or in the back, there's another screen with the same. So make yourself comfortable if you need to stand, whatever. Two, so many people mentioned they wanted more time to talk informally. We will have a longer lunch today. And again, you're free to step out and talk to anybody anytime in the hall, in the pub. There's even a private room. If you go back behind this room where the exit signs are, there's a little hall, but beyond that, there's another empty room and we have that reserved. So you're free to go back there. Let's see, number 3. If you submitted the comment about the Slido, somebody had a technical comment about how we could improve using the Slido, would you please talk with Elena? Because we are using it for the first time, and if you know a tip, we need it. Okay, another one. Let's see, the questions. Some people said the questions were a little too specific. We're going to be reviewing those, and we'll change them up if we need to. Another one is 1, 2, 4, all. Those of you that, some of you, it's new and it's uncomfortable, and I get that. I want you to invite you, if you are able to just get over the discomfort a little bit, you may find that in the time we have, which is 15 to 20 minutes, that's the fastest way to get input up and roll it up to Mark and the other people on the commission. Let's see. Oh, okay. For the people who just arrived, there's this concept called allies. We have allies. And I hope that everyone who already has an ally checks in with them early today, find out what your ally needs, tell them what you need, and look out for each other. So if you don't have an ally or your ally left, come see me and we'll assign you another one, or we'll find you another one. And then anyone who left their sheets with their ally information on it, I've got that information and I can give it back to you. Okay. That's all the announcements for now.
Okay, I've worked with databases across mostly the Western US and Mexico, and they led to a positive result of lowering risk to find resources. I mean, dramatically. So what I see is we have huge databases on Alaska, but no one has put it together into a narrative of the source, the process, the deposition, and where to put the drill hole, where to vector to the drill hole, and where to screen the different types of systems. So to me, that's the elephant in the room. Until we understand that, regulations, drilling, nothing makes any sense. We got to put it together into a geologic story that is predictive.
Right. Thank you.
I'll take a slightly different tack. I'd like to say Alaska has all the right people that it needs to answer this problem. There's not some whole new, discipline from overseas that needs to be brought in, or even from the lower 48. There are the resource professionals here in state. There are the regulators here in state that are very savvy with dealing with extractive industries. And I think it's just a matter of pointing that ship toward a new direction and plowing that new course. I don't know, do ships plow? I'm not sure. So
Thank you. What other table share your insight?
So we had actually it was Larry and Brad that came up with this. We had a slightly different insight, and that is that stimulated hydrogen versus naturally produced hydrogen could help de-risk the exploration for hydrogen, in that you have a more constrained set of circumstances that you're looking for initially, rather than the broader collection of circumstances you need for a natural occurrence to form. So that was an interesting insight from these guys.
Thank you. I can take 2 more from this side of the room. Come on. I'm going to pick on you if someone doesn't answer.
I had an interesting insight on the walk-in this morning, and that is that 12 months from now, there's a good possibility of half of what we've learned here today will be wrong. And that's all right, because this is what we're trying to do, is trying to figure this out. And we need to throw any ideas, even how silly it may seem at the time, on the table, and just accept that we're going to have to throw half of it away.
Good point. Anyone else? All right. Excuse me. Welcome.
We're building on another comment. I think the dramatic difference in time scale on how serpentization can take place versus oil and gas is a real paradigm shift and changes some of the potential exploitation mechanisms in a pretty dramatic way.
Thank you. If you've had any insight that is not up on Slido, you can put it in Slido. If not, if you've put in your one already and you don't want to edit it, you can always submit comments on the little 3x5 cards, which are in the box. And make sure you write legibly. We had a little trouble reading some of them from last night. And then also, if you don't mind, just put the session number on it so that we can sort them out easily at the end. Thank you. We really will read all these and we'll combine them all into the report that the USARC will generate. Steve, you're up now. Let me get my thing up.
All right, good morning, everybody. Still slippery out there. I almost lost it walking up from the parking lot. Thankfully, I didn't get a ticket last night. So yeah, as Mark explained, we're sort of moving along the chain, I guess, from the rocks into here was our first session is migration, preservation, and production of geologic hydrogen. So if I could have Haley and the speakers come up to the podium here, that would be great. And you'll see later on, we start getting into geologic hydrogen research later this morning and this afternoon. And that is where I said yesterday, we try to pull together a session on the interaction of geologic hydrogen and the cryosphere, and we're unable to do that because we couldn't find anybody who's doing any research on that. And so one of the key takeaways for the research that needs to be done is we need to look at the interaction of the cryosphere and geologic hydrogen. Anyway, I'll get off my soapbox and introduce Haley, who's right here on my left. And Haley Paine is the current Deputy Director for the Alaska Division of Oil and Gas, which would be one of the principal organizations regulating the production of geologic hydrogen in our state. So she is going to play a critical role in helping formulate those regulations. Haley's had multiple roles in the organization over the last 9 years, sorry. And originally she got her master's degree in natural resource management here at UAF and spent some time working at the Alaska Center for Energy and Power. And I've had some great pleasure working with Haley on a number of different issues when I was with DGGS and she was with oil and gas. So Haley, thank you.
Thank you, Steve. Thank you, Steve. Yeah, it's great to be back on campus. It looks like there's been some upgrades since I was here. The food has certainly improved, so that's lovely for everybody. I'm just going to pull up the speaker bios. I have the pleasure of introducing our panel today. In terms of the order seen here, we're going to do a little bit of a switch. We talked as a group in terms of the order and the story that we're going to tell. I think Dr. Myers did a great job setting it up, the foundations that we learned yesterday. And now we're kind of moving on to that next step of, how are you going to, find those right reservoirs? What is that trapping mechanism? And then over time, how do we ensure that that hydrogen is actually remaining in place? And so our speakers here today are going to kind of provide that review. And so to start us off, I'm actually going to read all 3 bios, maybe just to get started. I think Nettie did that yesterday. And I thought it was lovely to not interrupt the flow. I first will introduce, let me make sure I'm doing this in the right order. Yes, Dr. Josh Long. So he is currently a geologist with DNR's Division of Geological and Geophysical Surveys and Energy Resources Group, based at the Geologic Materials Center in Anchorage. He also was with the Division of Oil and Gas a little bit as well, so I'm going to add that to his bio. He completed a USGS Mendenhall postdoc working in the Alaska Basins and Petroleum Systems Group, and also was with 8 years with the ConocoPhillips, including 3 in Anchorage. After Dr. Josh Long, we're going to be welcoming Dr. Franek Hasiuk, who has a wonderful way to remind you of how to spell his name or pronounce it. It's Franek, which rhymes with Sonic, so thank you for that tip. He is a principal research geologist at Sandia National Laboratories who works remote from Kansas. He earned a master's and PhD from the University of Michigan in geology. His professional career has included a large oil company, Iowa State University, and the Kansas Geological Survey. Now at Sandia, Franek works on a variety of projects related to hydrogen, nuclear waste, geothermal, lithium, carbon capture use and storage, critical minerals, and road building materials. Of all of his professional accomplishments, he is proudest of his students the most. And then finally, we'd also like to welcome to the stage Dr. Alexis Templeton. She is a professor at the University of Colorado in Boulder. She leads an interdisciplinary research group that investigates the geochemistry and microbiology of water-rock reactions that produce hydrogen. Her team conducts hydrogen generation experiments in the laboratory and also identifies key hydrogen-producing reaction pathways in subsurface systems in the United States and on the Arabian Peninsula. Professor Templeton also characterizes the microbiology of subsurface hydrogen systems to understand what factors control the proliferation of hydrogen-dependent life. So thank you to all our speakers. And Dr. Long, I'd like to welcome you to the stage. Thanks. I know you have a stick. I don't know how you control it. There we go.
Okay. Yes, this little strange setup. It's nice. Good morning. I didn't realize we were adjusting the schedule until just now. It's my fault for not being here yesterday, but anyway, nice surprise. Get it over with. Have a discussion. So what I'd like to kind of cover is just a very high level overview of a couple of the better understood sedimentary basins in Alaska, and then just throw in a couple of the less well understood sedimentary basins in Alaska, and along with a bit of the reservoir characteristics that make a good sedimentary basin reservoir. To kind of start off with, I'm going to kind of walk over here and cheat a little bit. So this is a map of the kind of the better understood sedimentary distribution of sedimentary basins in Alaska, the Cenozoic, Mesozoic, Paleozoic, both onshore and offshore. And what I'd like to do today is talk a little bit about the North Slope, the Cook Inlet, and then a little bit less than I do the first two, but also talk about the Nenana and the Yukon Flats Basin. So these are less well understood, kind of smaller data sets, kind of more kind of frontier exploration kind of basins. I'm just going to walk through a couple of slides, kind of go over things that most of you probably already know, but to kind of cover the basics that I'm going to discuss in terms of the reservoir characteristics. First, provenance plays a major role in the composition of sedimentary reservoirs. And this is a function of the tectonic setting. This controls the lithology and the mineralogy. Just for example, kind of the schematic here. That's not a pointer. Sorry. You see the subduction zone, the development of the Four Arc Basin, and then a four-limb basin. So the upper slide would be kind of analogous to the Cook Inlet Basin in a very simple sense. And the bottom section is a four-limb thrust belt, so a four-limb basin, which is more analogous to what the North Slope is. And this composition, you can see in the ternary diagrams in the middle, the distribution of the terrains in Alaska kind of gives us a, not unique, but kind of a complex assemblage of sources for those provenance, for that material. So depositional environment is kind of one of the key factors in determining reservoir quality and distribution. This controls the sediment transport, which influences porosity and permeability ultimately, but also influences grain size and sorting. And then also you get to throw in the complexity of local, physical, and chemical processes. One item that's not on here is the geometry of the reservoir. So that's a big one too, both oil and gas, and I imagine hydrogen as well. Different depositional environments have different sand body geometries and different reservoir geometries. Thank you. Kind of following up on that, looking at distribution of porosity and permeability is largely a function of kind of a reservoir as a whole, but if you break it down to a smaller scale, it's strongly influenced by depositional processes. So even within a similar environment, say on the left, we have a deltaic system. Components within those deltas have different characteristics, so they're going to have different porosities and permeabilities. So that's kind of an added layer of complexity onto, say, deltaic or even fluvial systems in this example. Burial history is obviously a big one. It's compaction, later diagenesis, your shallow diagenesis, and then also hydrocarbon generation. This is a burial model from Yukon Flats, kind of showing the distribution and ages and burial depths, along with the timing associated with those burial depths. And then finally, the reservoir system as a whole, understanding the distribution of where the reservoir rock is, how the oil and gas or hydrogen in this case is trapped, how competent are those traps, how good is the quality of those reservoirs. So brief tectonic history. I wasn't here yesterday, unfortunately, so I'm sure some of this has been mentioned, but Alaska, as I said, is not Kansas, so it's a bit more complex. It's an assemblage of tectonic terrains. This assemblage, this process of assembly is ongoing. It's been going on for at least the last 200 million years or so. And all of these terrains have, maybe have a slightly different composition. You've got metamorphic rocks, you've got igneous rocks associated with volcanic arcs, you've got, metasedimentary rocks, and you have sedimentary rocks. So all of which, it makes it a bit complex, and it has to be accounted for on kind of a local scale. So starting with kind of the best understood of the basins in Alaska, up on the North Slope. The North Slope is the most recent iteration is a foreland basin, but it has kind of a complex history. The strat column on the left kind of shows the kind of conventional breakdown into the three mega sequences in the North Slope, the Ellsmerian, the Beaufortian, and the Brookian. And those represent distinct phases of development for the basin. Ellsmerian is more of a passive margin setting. You deposit the Lisburn groups, a lot of carbonates. Then you go into the Beaufortian, so that's associated with the opening of the Canada Basin. So you have kind of rift-related structures and reservoirs. And then into the Brookian, the most recent phase, where you develop the Colville Basin, which is a large, deep foreland basin associated with the thrusting of the Brooks Range. So it's fairly well understood. We have, according to AOGCC, I checked the numbers the other day, and 7,800 wells drilled since the 1940s. So that's a lot of data. A lot of data over a large range of time. So the quality of the data kind of is a function of the time, but also of the tools. So it's not just a function. You can't just say it's old, so it's bad. But you kind of have to know how to work with a range of data to get the most out of it. Good quality rocks, obviously. Average porosity range from 10 to 22, permeability to 10 to 265 millidarcies for some of the better reservoirs. And just a focus on the youngest of those three mega sequences. In the Brookian, this is kind of the interval of interest recently. So the last decade or so, there's been a lot of exploration associated with the Nunavik Formation. So that's an early Cretaceous, kind of non-marine to shallow marine facies or lithology. And this was deposited in the Mesozoic and Cenozoic Foreland Basin. So the Brookian strata is quite thick. Not the Nunavik itself, but the entire Brookian section is up to 25,000 feet thick. And there's potentially decent reservoir rock within all of that. Within the Nunavik more specifically, if you look on the bottom right, this is a plot of mean porosity versus maximum burial depth. Due to the composition of the Nunavik, burial depth is seen as one of the primary reasons that you decrease reservoir quality. And it's a function of its composition. So there's more ductile grains in a Nunavik. Therefore, compaction is going to influence it more strongly than, say, some other reservoirs with different compositions. So jump down to the south of the Cook Inlet, different tectonic setting. This is there's a location map on the top right to kind of keep us oriented if you don't know where these are. But it's a four-arc basin, so it's associated with the subduction of the Pacific Plate to the south. And develop this four-arc basin into which 20,000 some odd feet of non-marine sediment was deposited since during the Cenozoic. And it's important distinction to make that distinction between the depositional environments, between the non-marine sediments, dominantly non-marine sediments, and the kind of combination of sediments you see on the North Slope. So different reservoir quality, different reservoir geometry, different trap quality, different trap kind of geometries. So because the Cook Inlet is around Anchorage, so it's fairly accessible. There are decent quality outcrops that kind of rim the entire Cook Inlet. So we have a reasonable handle on particularly this Triassic to Jurassic into early Cretaceous kind of section. It's easier to study than most of the Tertiary. Tertiary does outcrop along the margin, but the Cook Inlet as a whole has a bit smaller data set than the North Slope. So we have, I didn't put the number up here, but I want to say the number was closer to 3,000 to 4,000 well penetrations. Somebody can correct me if that's off. but not quite as good of a data set. And even within those younger sections, most of the gas production comes from the tertiary. And there's a wide range of reservoir quality associated with the tertiary with the several formations within the tertiary, due to the range of the distribution of the provenance areas. So you're getting input from multiple sides of the basin that have different compositions, and that's going to affect the reservoir quality. To kind of jump to the interior of two examples, these basins are less well studied, much less control. This is the Nana Basin. You can see it up here on the right. This is, we're pretty close to it right now. This is the study from Ridgeway. This figure on the left kind of shows the stratigraphic position. So this is the thickness of the strata within the Nana Basin. And an interesting thing that the study showed was that there's a switch that happens around where that dashed red line is. And that switch in reservoir composition, and therefore the control in the quality, is associated with a drainage switch that happened associated with the uplift of kind of the mountains to the south. And then Yukon Flats. Yukon Flats is another interior basin. These interior basins are kind of extensional basins, my understanding. Maybe someone can correct me. I think they're generally transtensional basins. They can be fairly deep, but they're not quite as big as, say, the North Slope or Cook Inlet. The thickness and the reservoir quality of the rocks that are contained within Yukon Flats is pretty poorly constrained. USGS did a bunch of good work in the early 2000s on kind of modeling the oil and gas system in Yukon Flats. And one of the products of that study was this cross section here on the right, kind of giving you a very general sense of what that basin looks like in terms of the distribution of strata, and also the kind of the lithology of the sections around it, to get a better handle on the composition. So just to sum up, just a few kind of key takeaways. There's a wide range of reservoir quality. Reservoir quality can be outstanding, and it can be horrible, and that can be a function of sort of local variability in provenance, mineralogy, and burial history, right? So these more focused or more local variabilities are a factor in reservoir quality. Some of them, there's a range in data sets from the North Slope and Cook Inlet to the Nana and Yukon Flats basins, but most of which have pretty good reservoir quality, at least somewhere in the section. And one of the biggest hurdles with the interior basins is just the lack of data sets. So it is kind of frontier rank exploration, right? They do exist in an area where you can kind of study everything around it, but the data from within the basin itself is pretty sparse. And I think I'll stop there.
Thank you. So I'll just go ahead and pass this on to you, Franek.
All right. Good morning, everyone. Is there a clicker? It's up here. Okay, cool. All right. Hi, my name is Franek Hasiuk. I am the one here, I guess, who has to defend Kansas because there's been a lot of Kansas trash talk this morning. I live in Lawrence, but I'm a remote worker for Sandia National Labs down in Albuquerque. I'm maybe the closest one living to an active exploration play in hydrogen, maybe in this room. I don't know if there's anyone else from the Midwest here. Raise your hand. Okay, we got a couple. All right, yep. But it's really exciting. There's a lot of sort of behind the scenes, quiet, but fervent exploration activity in terms of drilling wells, leasing land. There's a lot of questions. There's a lot of unanswered questions about what hydrogen means for businesses, for governments, for regulators, for the general public. And I think that we can start communicating that answers to those questions in ways that can be a little simpler and a little broader, and we can base those in some of the activities that are already going on in a lot of the places that are looking or prospectively looking for hydrogen. And so that's sort of what I'm going to talk about in this presentation, just trying to put hydrogen reservoirs in the context of other activities that we already do. Because one of the things that I've experienced in talking about geologic hydrogen from national conferences all the way down to, the Kansas Independent Oil and Gas Association, is people think that, the first thing they say is, what about the Hindenburg, right? And then the second thing they say is, oh, it's so small. How can it stay anywhere? It doesn't just float off into space. But I think there's some really effective ways that we can just say, no, like, let's like sit down and talk about this in the context of all the things that we already do in terms of resource extraction. So, okay. All right, so here's my summary. So geologic hydrogen can be preserved in the subsurface on geologic timescales and on human timescales, like other natural gases and liquids, and even some unnatural ones. So in Kansas, one of the things that you may not know that we do is that we have a very vibrant industry in storing refined hydrocarbons in salt caverns. So we have a big layer of salt called the Hutchinson salt that covers about the southwestern half of the state. And there's 700 salt caverns that have been built into that. Now, these are pretty small compared to the big Gulf Coast ones you might have heard about that you can fit the Empire State Building in. But these are commercial activities where they are storing refined propane and butane and ethane today. And this has been economic for decades, right? And so these are the sorts of activities that people may not know about, but there are ways that you can sort of talk about how we do store energetic liquids and gases in our subsurface today. And you probably haven't heard about it because there have been not that many incidents related to it. Okay, so natural hydrogen can be preserved in pore space and fractures. A lot of times we only think about natural hydrogen maybe in the pore space of a sandstone or a limestone, but we can have fracture porosity, right? We have examples of fractured basement oil reservoirs. One of the first one I learned about was offshore southern Vietnam. There's a big oil field down there where it's fractured granite basement. But you can go to the central Kansas uplift, and there are oil fields that have been charged from deeper basins, but they are in fractured granite at basement highs, okay? Stimulated hydrogen, over geologic timescales, we can think of that, if it escapes off into some sedimentary reservoir, we would call that natural hydrogen, but it's preserved as, reduced iron in those original source rocks, right? And that sort of serves as its own cap rock. And you can sort of think about that, maybe there's some foreshadowing there to another type of resource that we know is trapped in its own source rock, something that's been very valuable and very lucrative over the last 20 years. And then finally, stored hydrogen. This is very analogous to what we do. We can store hydrogen in the subsurface, either in porous media or in salt caverns, right? These are ways that we can have large amounts of hydrogen in the subsurface, either from natural activities or from human activities. Okay, and this is how I like to visualize it. One slide, just a couple words. We've got our big cloud that represents all the hydrogen reservoirs in the world. And my perspective is that we've got three ways we can think about that. One is that we've got our hydrogen storage, right? These are reservoirs where humans have made hydrogen or found it somewhere else. They brought it somewhere and they say, we need a big store of hydrogen right here for some reason. Maybe it's industry, maybe it's providing heating fuel to a local community, but there's a reason we need to store a lot of hydrogen somewhere. In the upper Midwest, we need to store natural gas locally because we don't want to have pipeline interruptions in the winter when it gets really cold, right? Though it's not as cold as it used to be. Right? We have natural hydrogen, and that's where we just pump hydrogen out of the ground from some subsurface reservoir. Again, pore space, fracture pores, one of the two. And then we can stimulate the production of hydrogen, and that's where we need to inject something that's not hydrogen to get hydrogen out. That fluid we inject is probably largely water-based, and then we would get hydrogen back out. And what I really love about this model of thinking about subsurface hydrogen reservoirs is it tracks very closely with what we've done with natural gas for the last 100 years. We've stored natural gas in the subsurface, we've produced natural gas in the subsurface, and we've stimulated natural gas out of the subsurface. And I apologize, those should say natural gas at the bottom, not hydrogen. I just missed that edit this morning, I guess. But in this way, right, If we had done this 20 years ago, I wouldn't have maybe had that stimulated bubble there, right? Because 20 years ago, we didn't think shales were that important in our energy mix, right? When I was in grad school, I was in the library getting a book on something else, and right next to it, I saw a book that said Sedimentology of Shale. And I was like, holy cow, I don't think anyone's ever taught me about shales. I better grab that and go read it. Later that day, my advisor saw it on my desk and picked it up like this and said, what are you doing with a book on shales? There's no reason anyone would ever want to study shales, right? Tenured, full professor. We've already said the University of Michigan, right? So this isn't just like some small agricultural school like Ohio State or something. I only do it because I love you, Don. But like that's one of the issues we have to remember, is that there is a certain amount of received wisdom out there, right? Conventional wisdom, and we have to be willing to go beyond that, right? Shale, stimulating the production of natural gas from shales and other unconventional resources has dramatically changed the energy landscape of the whole planet, right? And that's where I think, you know, maybe hydrogen can be that next revolution, okay? In terms of our different kinds of subsurface reservoirs, I've made this chart with technology readiness levels. This is a way to sort of describe how commercial a technology is. Is it operating? Do we have private companies doing this on their own now? Yes, for storing hydrogen in salt caverns, we do. So we store hydrogen in the subsurface. There's a certain amount of hydrogen industry already out there, right? Stored hydrogen in porosity or porous media, that's sort of a 6 on the scale. There's been some tests in Europe of relatively small scale injections, studying the geomicrobiology, the effects on materials, all that sort of thing. Where we are with stimulated hydrogen, we're still coming up that curve. Like, we know what the right source rocks are, right? Or we theoretically know what those correct source rocks are. We talked about a lot of that yesterday. Natural hydrogen, on the other hand, we're pretty low on that. We don't quite know. If someone said, hey, I'm going to give you some money, go drill a well. And people are asking that question across Kansas, Nebraska, and Iowa right now. There are big investors coming in saying, hey, we want some really cheap hydrogen. Where can we drill? We don't know where to go yet. We have some ideas. We have some guides. A lot of the really good information is highly proprietary. But there's still a lot of work, a lot of room to advance these technologies all the way over to that 9, where we have a vibrant private industry that's effectively regulated to protect the environment and to support the communities that those activities are operating in. This is just a little graph that I have here. One thing I want to again impress on you is that we can have pore space in those basement rocks, right? And so we shouldn't forget that those can be a reservoir just in the same way as pore space can. We can use that same classic exploration method from the oil and gas industry that we heard yesterday about, where we go from basin scale analysis to refining our prospects all the way down to something that we can drill, something we can appraise, and something we can develop into a producing asset. And I'm just going to skip that and go to this one. And one thing I do like too is charts that compare a bunch of different things at the same time. And so one of the most important properties of any reservoir is its permeability. And I really like this chart because it shows us that if we have unfractured igneous and metamorphic rocks, they're among the least permeable rocks that have been measured by science. But if we fracture those, we can get highly permeable systems, right? And that's good if we want to stimulate hydrogen production. That's good if we're looking for a fractured basement reservoir, okay? And then I've got all the different units there on the bottom, depending on what kind of scientist you are, you measure permeability in different ways. And then finally, I just have my summary up here again. I thank you for your time, and I look forward to any questions that you have. Thanks.
Thank you. Thanks for looking out for Kansas there. I think they really appreciated that. All right. And Alexis, turning it over to you now. When we were chatting prior to this panel, Alexis just said something that really had resonated with me, and that was just that, you know, it's not just about how, you know, what's down there, but how hungry are they? Are they going to get full fast, or are they going to keep eating? And I'm like, so is it like my son, where it's like you just give him 2 bites and we're done, or is it my daughter who's going to eat everything that we've got? And how do we kind of balance those guys against each other? And that also really echoed with another comment at the table yesterday, which was our ability to predict that sort of, you know, gross amount of hydrogen versus your actual net. And so just maybe one question while we're waiting for other folks to type in their questions on Slido, just to kick us off along that. I think you sort of left the door open there at the end, Alexis, but how will we improve our predictions for the preservation of hydrogen? You know, there's a lot of gaps there. What do we need to do? What are those sort of next steps to understand that a little bit better?
I mean, it's definitely, we need a lot better models of these systems at the moment. So it's been really interesting. I've had the good fortune to work with Jeff Ellis this year and his colleagues at Colorado School of Mines with Yaoguo Li and Mengli Zhang. And in their consortia, they're working with other companies like this company, Taranta, that's trying to help them build hydrogen systems models. And and you really start to see the data gaps that are needed to understand aspects not only of production and migration, but what would be some of the reactive consumption that could occur in these reservoirs. And there's other companies and groups that are working down these roads. And as we build those models that can really include the reactive transport, the issue is, again, these big data gaps on like, what are the real rates? Both how fast can production go? That was a big question yesterday. How fast can you make hydrogen? But this same thing, how fast can you consume hydrogen, and when will you turn that up or down? And the range, the dynamic range, is more than 6 orders of magnitude. So we have a lot of data that we've put together now that's just really showing how fast and how you can titrate that. So we need to validate that in some more field systems, but I think it'll be really important for this de-risking aspect is much better modeling.
Okay, great. Thank you. Coming in quick here. So maybe we'll go with this one. This looks like it's directed towards Josh. Have you found any well logs with greater than normal free hydrogen in Alaska? Have we looked?
Really short answer. No, I haven't. No, I don't know. Maybe Melanie can address this, but as far as I understand, we don't have kind of an active exploration part of our program for hydrogen. Is that a fair statement?
Yeah, sure thing.
No.
Thank you. Okay, so it looks like we got a few different ones coming in here. I'll just put this one out. Let's see. Sorry about that. What are the temperature boundaries on bacterial growth?
Great question. So the known temperature limits for life are around 120 degrees C. You don't pasteurize it, like sterilize if you go hotter than that necessarily. There's a lot of ways that microbes living in rock matrices can still be survive that, and then temperatures can cool. But somewhere in there, you crack 120, you really shut down activity. So again, Jeff Ellis had a nice slide in his talk in the pub last night that came from, I think, this guy Laurent Truche. But it just sort of shows this, there's this dream that you can go to 100 to 200 degrees C and kind of find all the great conditions for production of hydrogen, but not loss as much. But there are a series of abiotic reactions that will increasingly compete for consumption of hydrogen as you go higher. So it's hard to find that window where you can really block both of them out.
Franek, I know in a lot of your discussion you talked about, obviously salt caverns, but just maybe more broadly, like what are the high level criteria to consider for hydrogen site selection for storage?
Excuse me, I think those criteria are in many ways very similar to other sorts of gas accumulations in the subsurface. If we're looking for natural hydrogen, it's having a good cap rock, whether that cap rock is a sedimentary cap rock like a shale, whether it's a salt, whether it's like in the case of Mali, an igneous rock. Like we have to keep our aperture really wide in terms of what our potential cap rocks could be. And I think we saw from Alaska, there's a lot of sedimentary rock just on that level that can be investigated, that can be explored for accumulations. The question, I would say is there anything from the biological side that would help us narrow down, if we have a basin with 20,000 feet of sediment in it, do we need to drill all the way to the bottom? Are there ways we can high grade where in a sedimentary basin to look or not look for natural hydrogen at least? Alexis, do you have an answer?
My own voice is on or not. Oh, there it is. Okay. So let's see, kind of going back to a little bit of the North Slope questions here. And I understand we haven't seen, the direct well results as you indicated already, Josh, but can you comment on the prospectivity of Southern North Slope for hydrogen storage? Parts of this well-studied basin away from oil source rocks could be suitable.
Yeah, I think, well, most of the field work that my group does is in the foothills. So we're much further south than the established reservoirs and producing areas are. And in terms of the components of a functioning reservoir system, all those things seem to be in place. There is a bit of a risk because you are closer to the foothills. So those reservoirs could be in direct connection to the atmosphere. Right, so you've got, and the structural complexity is a bit higher than most of the North Slope fields. But other than that, the other challenge is extrapolating from the outcrop work that we do to the subsurface data sets. Right, it can be done, but the data quality is generally lower and much more sparse. But in terms of overall potential, I would say, yeah, there is potential.
Then going back to Alexis, how does microbial observations inform us about timescale when you say 4D characteristics? I think timescale has been a popular topic this morning and yesterday as well.
Yeah, I think it connects. I mean, I'm seeing all these questions come by and I go also like with methane, could it be a clue to finding? Yeah, good. No problem. Yeah, let's do that one. That's good. Yeah, I'm going to kind of integrate a couple of the questions I'm seeing coming by. So like when it says, do you think existence of methane may be a clue for geologic hydrogen? And I think so. So personally, I'm staking it. I'll argue with all the isotopists out there that they keep calling stuff abiotic methane that is not abiotic. And so we will definitely show some works where we can make biological abiotic methane. So let's be careful. We got it. Like when we see methane, it's like, where did it come from? So if we go into some systems that are shallow, we see a lot of methane, and I think it's recent, comes to the 4D part, that form from a hydrogen flux coming up from below. And if we do have this challenge of not really being able to sense hydrogen as well as we want in the surface environment, I think, because a lot of transformations occurring in those upper 100 meters of these aquifers and before you get to the soils, we need to go into the deeper subsurface. We have to get down hundreds or thousands of meters, depending on the system that you're looking at, to really look at what the hydrogen dynamic is that's happening. That's a personal point of view, but I really think that so much biological activity on the surface is giving you other signals. But if you go look for methane or sulfide, that's great. It might tell you that there's a hydrogen flux deeper, but you want to go to the source. Go down there and look at the dynamic of what's going on, would be my suggestion.
And nobody needs to hear speakers.
Yeah.
There's one that's got a thumbs up there in the bottom. Maybe anybody on the panel can take this one. Do we think oil and gas is the closest existing established industry with relevant exploration and excavation technology for geologic hydrogen? Or there's others that we just haven't talked about yet today or yesterday? That's for anyone up on the table.
Most of my experience is limited to oil and gas, so I'm not sure I can comment on that. Franek?
I think it's very obvious to say oil and gas. In the realm of stimulated hydrogen production, if we're talking about sort of the model where you're going to have an open pit mine and you're going to mine our ultramafic rock, crush it into some fine powder, and then react that, I think that's more of the mining industry that we would want to be thinking about in that respect. And certainly operating an open pit mine, that's their expertise. Certainly looking at the extractive industries in general is, I think, the best way to think about this industry and where we might want to pattern regulations for it off of.
Up there as well, but I didn't know, as you all seen any jump by, if there was any that stood out to you that you really wanted to touch on and that raised another relevant point. I could also bring up one that I think Alexis talked about herself, but didn't have an answer for. But I love that she suggested something that she didn't have an answer for. I think that's great. And so it was, of course, now I'm going to lose it. But basically, how could we harness microbiology to be more beneficial component of hydrogen systems production? Like, we've been thinking about the paradigm, how can it impact it negatively, but how can we find this in a positive way?
Yeah, I mean, in many ways, it comes back to, I mean, I find it so interesting. We've tried to study these systems because it's so exciting to us that they were alive. Hydrogen, wherever hydrogen's produced, that life is existing in the subsurface of our Earth. So that's been a sort of fundamental interest. And now everyone wants to kill the microbes and obliterate them to make sure that they won't eat all the hydrogen. And you can't do it. You're not going to be able to sterilize these systems. You can suppress them or divert them, but you're not going to be able to kill them. And then when I go to France or other places, they're all just like, why are you not talking about protecting the subsurface microbiome? What are you going to be doing with our new adaptations of extractive industries to changing how the subsurface functions as an ecosystem? And so it's a complex sort of interweaving. One of the good things to know, though, in my mind, is that we do not want to be leaking hydrogen to the atmosphere. We don't want to have the atmospheric impacts of hydrogen as a greenhouse gas, or both its side and direct effects. So we are going to need to sense where leaking's happening. There's a lot of technology being developed by DOE for that right now. We also need to be able to stop it if it's happening. Well, and that would be a great example of where we could be looking at how do you stimulate microbial activity to consume hydrogen long before it crosses from the subsurface to the surface interface where you're working. So I think if we can keep understanding how it's integrated into the system, we can both think about how to protect the environment and to create beneficial technologies that connect to it.
We're going to want to continue. I think the mics keep getting turned down a little bit. How are we doing there?
Oh.
I think it's a battery issue. Because they're set to on, and now it's back on again. So I think when they just kind of keep flicking off, or we're just holding them extra tight and clenching. Oh, okay. Sure thing. Okay, we do have a break coming up here in just a little bit. Let's see. So I think the hand in the back was to let us know that we needed the microphones up, but just making sure there weren't any other sort of questions. Somebody was just couldn't get the attention on in there. Okay, great. Let's see here. So I was wondering, Franek, if you could talk a little bit more about, this technology readiness level of 9, for hydrogen salt cavern storage. Perhaps just showing my naivete here, but I know that, we're talking about the potential properties of hydrogen, how it could be corrosive or it could be caustic, and these different things that it could do. And so in terms of that readiness level, like, do we have, as a result of some of our experience in the salt cavern world, the type of tools, metals, materials, drilling equipment? I mean, are we actually ready to implement that at scale if we are going to start kind of continuing to advance this? So I was wondering if you could share about that.
Sure. So in my discussions with one of the hydrogen salt cavern operators, as well as with several pipeline operators about running hydrogen through their materials, they are concerned about legacy materials and their reactivity with hydrogen. Hydrogen is very small, it can embrittle steel. All of them said, though, if we design a system from the beginning for hydrogen, we can do that today. And that's what they had to do for the salt cavern, the one that I talked to that's on the Gulf Coast. And so that we do have the technology to build something new for hydrogen. I think that one of the other technologies we need to develop is a microphone that stays on. Yeah. But what I will say is that, where's I going with that? Okay. Is this microphone? Oh, all right. So we're just going to.
Sorry, the reason we have to have the mics on is for the Zoom recording, because we're recording so it isn't just so you guys can hear. So I'm going to charge this and see if that helps.
But one thing we want to think about in terms of infrastructure, is we need to develop technologies to be able to use that legacy stuff we already have in the ground. Otherwise, we will need for hydrogen to build out an entirely new infrastructure that what we have today took us 100+ years to put into ground. You know, is the federal government going to come and just write that check? I doubt it. Does industry have all that money to do that by 2050? I doubt it. So we definitely need those technologies that say, you know, for the steel in this particular well or pipe, what's the remediation so that we can use it with a hydrogen system? Is there a coating we can put on the inside of the pipe? Is there some other constituent we can add to that gas to make it less corrosive? What is the thing we need to do? Is there, you know, some electrical system that we can put in there that can help, you know, stop that corrosion from happening? Yeah. Right. Yeah, so Don just mentioned that there are a lot of steels that are out there and other materials that are currently rated for hydrogen applications. A lot of them aren't already in service in a lot of our pipeline infrastructure, but that doesn't mean that if we were building something new that they wouldn't select those materials. And right. Okay. So just for the microphone, Don said that there are some existing materials that do just fine with hydrogen as long as it, you know, it doesn't exceed certain operating conditions. And I think that's a great point to make. You know, another thing too is we can, I'll just say from my perspective, I've experienced a lot of people saying no, hydrogen won't work, but we also have to remember that if it doesn't work, what's the next thing? Like we want to decarbonize. This is one of our options for decarbonizing. It should probably go into that basket with a lot of different things. We don't need hydrogen to do everything probably, just like we don't have one source of energy today in our country or in our world. Hydrogen's probably going to make sense in certain places in certain applications, just like hydropower makes sense in certain places, nuclear makes sense in certain places, wind and solar make great sense in Kansas, right? Certain things work in certain places, and I'm just excited to see where hydrogen is going to fit into all of this because it's got a lot going for it, and certainly if we can use that existing infrastructure, that's going to be a big leg up on meeting those decarbonization goals that we've set globally.
And maybe we'll just get to one or two more here. And so this one's really for anyone just kind of looking at the last one up there. Do you think the existence of methane may become a clue for finding geologic hydrogen?
So I kind of grabbed that one earlier, but I'm happy also if the people want to, no, it's okay, but if people want to debate that or not. I mean, again, depending on the reservoirs, I mean, look at how we have a challenge when we have hydrogen and helium in a reservoir and we're trying to understand, do they come from two different sources or the same one? And then when we just look at methane, methane is almost always coming from multiple sources when we're finding it. And that's one of the biggest challenges in unraveling it is it's not just it got produced through one pathway, it's come from a variety of sources. So we do still need to find some way of potentially recognizing is methane maybe being actively produced. And that would be more of a sense that there's a hydrogen flux here and it's being converted to methane. And that is where I will give the isotope geochemists a good happy thing with like clumped isotope systems, allowing you to see the kinetic disequilibrium that's preserved still in those molecules. It can be really helpful to be like, oh, this is forming under a condition that actually may be in part biologically influenced, some fraction of it. So we're really looking at what are the tools going to be that you come in and sense as best possible with a few samples, the dynamic that's happening deeper in the system, and where might there be hydrogen being both, again, produced and consumed, what that balance looks like.
All right, thank you. And then perhaps for our last question, we'll go to the back of the room here to Jeff. Okay.
I guess the reason I put it there, I'll repeat the question. Jeff Ellis asked me why I put the TRL of natural hydrogen at 1 rather than, I guess, what published literature has said at 5. And I guess I would say we haven't, there is the example at Mali where you could say that's a pilot, that's an operating system. I would say it's a relatively small scale system. It hasn't been, how do we scale that up, right? How do we have major industrial activity around natural hydrogen? And I just don't think we've found that big discovery that sets off, you know, we haven't had our Western Pennsylvania moment. We haven't had our Spindletop. And then when we have that robust, like, yes, a 9 would be, we've got our full commercial industry going. But for natural hydrogen, it's my perspective that we just haven't had enough exploration successes to call in it as an industrial activity anything other than a low number. I could go up from 1, but I don't think I would want to say 5. And that'd be a great question to actually have a beer over and discuss. Right, but I think we know where to go find the rocks. We know the source rocks, right? We know there's a map of ultramafic rocks of Alaska. If someone said, hey, I want you to do a hydrogen project in Alaska on stimulated, I'd pull that map out and that would be my ranked list, right? If someone said, where do I go drill for hydrogen in Alaska? I would say, that's a harder question to answer. I would have to get the basin map that Josh just showed, and I would have to narrow, it would be a more complicated activity. Yes. Right. Oh. So Jeff just said that me saying that I could just go to any ultramafic rock and stimulate it is a simplification. Completely agree. I'm a limestone geochemist, right? I know about calcium, I know about carbonate. But what I meant by that was I would say, if I want to do a stimulated project, we've got that map of where these deposits are. Not everyone will be perfect. There's going to be a ranked list that we make after actually looking at chemistry and, you know, a bunch of other things. But at least we've got polygons on a map that we can go to. And so that's why I would say, and I may be completely wrong, and even if people think I'm right today, as the gentleman over here said, in 12 months, I may be also completely wrong, even if I may be somewhat right today. That's where I would put it, because if someone said, go put an X on a map of where to go do a project, I could be more confident in picking something from that ultramafic list today. In 12 months, maybe we will have figured out what basins in Alaska we want to go drill, right? If we're on the Mid-Continent Rift, I would probably be more excited about putting an X on that than trying to talk about ultramafic stimulation. And so again, it may be very geography dependent. In Alaska, maybe it's the TRL of stimulated play is higher, but in the Midwest, natural hydrogen play, the TRL is higher because we've got, you know, better economics on drilling. There's private industry activity, stuff like that. So, but I'd really, you know, I want to see that big one. I don't want to see a blowout for sure. No one wants to see a blowout. But what we want to see is that big discovery, that big announcement, that SEC filing, and then we can start saying that we're marching up that TRL ladder. So, in my opinion, and again, I will say in my opinion, I'm not claiming to know everything. I'm just hoping that I know. I'm maybe standing on a little bit of something. I don't know. So,
I think it's a great debate. So I'm glad that debate got started.
You do know everything. You're on a panel. Well, in my opinion, that was really great. So thank you all. Can we have another hand for our speakers today and presenters? All right, wonderful. I'm turning back to our MC.
All right, folks. I would like every table to either choose or someone can volunteer to be the discussion leader for this section. We need to have a clear leader. So please do that. We're not taking a break right now. We'll take a break soon. Although I want you to make yourselves comfortable. Okay, let's get going. We're on page 12 of your 3-ring binder, the table guide. Whoever's the leader, please read that. Just give it a skim. Okay. Those who are having conversations now, could you please take your conversations to the hall? I love the conversations, but please take them out to the hall. Thank you. All right, so our question this morning is, what are the challenges regarding migration and preservation of geologic hydrogen? We're going to use the 1, 2, 4 all again as written in the book. We're going to give it a good try, the way it's written, and see how that works. Page 12. So for 1 minute alone, I'd like you to think of answers to the question. What are the challenges regarding migration and preservation of geologic hydrogen? I will start the minute now. All right, a minute is up. Thank you very much for respecting the needs of people to be quiet when we're thinking. Okay, next one, 2 minutes in pairs. Find a partner and just 1 minute each, share your initial thoughts. And after that, we'll go into fours, but we'll do the 2 minutes and I'll let you know when 2 minutes is up. When 2 minutes is up, one pair will join another pair. Or if you have 5 at a table, that's okay too. I don't want to interrupt the thinking, but we'll start with the 2 minutes. I'll signal you and then you move into fours.
So our next session is Geologic Hydrogen Research Part 1. And this is where we're going to be taking a slightly bigger picture view of hydrogen research around the world that's being conducted. And the second session on research is going to delve into more specific research that's being conducted within the United States on geologic hydrogen. And the moderator for this first session is Dr. Robert McCoy, or Barb McCoy, as we all know him. Bob has been director of the Geophysical Institute for the past 13 years. Prior to that, he worked for the Navy as a space scientist for a few decades in the Naval Research Lab in the Office of Naval Research, where he built and flew instruments on rockets, satellites, on the space shuttle, the International Space Station. So Bob is an actual honest-to-God rocket scientist. So he has degrees from physics at Cornell, Texas A&M, and a PhD from astrophysics at the University of Colorado Boulder. And without Bob, this meeting would not be happening. When Mark and I met with Bob back in March or April, I think it was, I don't remember exactly when, and floated this idea of this meeting to Bob, Bob was extremely supportive and subsequently made his financial resources, his intellectual and logistical resources available for this meeting. So without Bob, I feel it fair to say this meeting would not be happening. So thanks, Bob. It's great.
Thanks, Steve. Yeah, Steve said I'm a space guy, that most of my career doing ultraviolet observations of the Earth, Mars, planets, comets. And all you see in the ultraviolet is hydrogen. It's kind of unrelated to what we're talking here. I'm learning a lot here about H2, but in space it's all atomic hydrogen. And you can see, take an image of the Earth, atomic hydrogen, the geocorona extends halfway out to the moon. It's fascinating what I'm learning today, but there's also a lot of other stuff going on in this area. So this is going to be an exciting session, exciting 2 sessions where we look at what's the state of research around the U.S., around the world, and hopefully we'll get an idea of what's been done and what hasn't been done. But I want to introduce our speakers. I'll introduce all 4 of them. At the second from my left is Jeff Ellis. You've already heard him talk twice. This is his third talk. But he's a petroleum geochemist with the Energy and Resources Program, the ERP of the USGS. He manages the seal tube and hydrous pyrolysis laboratories within the Center of Energy and Resources Center, Science Center. He has a BA in Geological Sciences from Cornell, which is my alma mater. He MS in geochemistry from the Colorado School of Mines and a PhD in marine geology and geophysics from the Rosenstiel School of Marine and Atmospheric Science at University of Miami. And he'll be talking about the historical context and overview of the rest of the world. Next is Dr. Doug Wicks, here on my left. He's a program director for ARPA, the Advanced Research Projects Agency Energy. His focus at ARPA-E is on waste to energy technologies. He has a BS in chemistry from North Dakota State University and a PhD in polymer science and engineering from the University of Massachusetts, Amherst. Next, Canada, we have Dr. Omid Ardakani. Hopefully I said that right. He's a research scientist with the Geological Survey of Canada. He has an MSc in sedimentology and petrology from the University of Tehran and a PhD in carbonate geochemistry from the University of Windsor. And finally, Dr. Teppo Arola from the chief expert of Geological Survey of Finland. He has a master's degree in geology, earth science from the University of Turku and a PhD from the University of Helsinki. And he'll be talking about natural hydrogen research example from Finland. And I guess we're starting off with Dr. Ellis. How this works.
Thanks, Bob. So I'm going to set the stage here by giving us a bit of historic context about where did we first start to think about natural hydrogen on Earth, and then how research ideas have evolved around actually the natural hydrogen as a potential energy resource. We can get these to advance. I have the worst luck with this advance. Oh, there we go. Okay, so we've known about flammable gases coming out of the Earth's subsurface since antiquity. This image in the lower right is of the burning gases at the famous Chimera site in Turkey. But it wasn't until the late 1800s that we actually knew what these gases were, what the composition was. And in fact, it was the famous Russian chemist Dmitry Mendeleev, sorry, who he's of course famous for the periodic table of chemistry, but he was the first one to actually measure the composition of a gas from a coal mine in Ukraine and discovered that there was several percent of hydrogen in those gases. And he and others actually were, he and others in the late 1800s, early 1900s, had proposed that petroleum, in fact, was generated through abiotic processes in the deep subsurface through reactions of hydrogen with carbon deep inside the Earth. And actually, from the mid 20th century through the late 20th century, there was a large debate in the petroleum geochemistry world around the source of petroleum and whether it could be sourced exclusively from biological rocks or organic rich rocks through generative processes, or whether it was this abiotic process. By the end of the 20th century, the overwhelming evidence has shown that the vast majority of hydrocarbons are from a biologic origin. They're from organic rich rocks. That this notion that you could have significant amounts of synthesis through like Fischer-Tropsch or Sabatier processes, that this is just not happening on the kinds of scales that would generate all of the oil and gas that we find in the world today. And I'll just also point out that that part of that thinking about the abiotic hydrocarbons was this idea that there's huge amounts of hydrogen inside the Earth's surface, as exemplified by this publication from Vladimir Lerin. Again, he's a Ukrainian geologist, and I think that that in disproving the abiotic hydrocarbon theory, a lot of people dismissed this idea that there could be large amounts of hydrogen then in the subsurface. And in fact, those two ideas are they're not coupled. That the fact that just because hydrocarbons aren't made from hydrogen recombining with carbon in the subsurface, that doesn't mean that there's not then large amounts of hydrogen in the subsurface. But we really hadn't given it much thought about hydrogen being in the subsurface as in resource sort of quantities until the early 2000s, when Nigel Smith and his colleagues at the British Geologic Survey published a few papers in conference proceedings, as well as a couple of other articles saying that, hey, look, we haven't really taken this seriously, and there could actually be hydrogen, and we just haven't really been looking for it in the right places with the right tools. But that really didn't get much traction. There wasn't really very much interest at that time, except a few researchers in France, primarily at the French Petroleum Institute, Eric Deville and Isabelle Moretti and some of their students. They began working on this sort of in the early 2000 time frame, and they were kind of working on their own out in the wilderness, following up this idea that maybe there could be hydrogen in the subsurface. And then we had this accidental discovery of an accumulation of hydrogen in Mali, and then the subsequent exploration campaign that was conducted there to assess how much hydrogen would be in place and how it was being trapped there and so forth. And in the period around 2015, 2017, there were some conference papers that came out talking about the Mali discovery and the importance of this. And then the 2018 paper from Alain Prinzhofer and his colleagues was the first peer-reviewed publication to talk about the Mali discovery. And that, I think, really was a catalyst that got the attention of a broader geoscience community saying, hey, there's something here. We really just haven't been looking at this, and we should start to think about it. And then another important publication shortly after Alain Prinzhofer's paper was this very comprehensive review paper from Vyacheslav Zagonek in 2020 that, if you're not familiar with that, it's sort of the foundational work that people rely on to understand what we know today about the occurrence of natural hydrogen on Earth. And so since the Prinzhofer paper and interest in this has started to grow, and we have companies now exploring, the research has really taken off. And primarily it started in Europe. The French, we have a list there. This is not comprehensive, but it lists some of the major French institutions that have very active research programs today looking at geologic hydrogen. But it's also spread to Germany and the UK, and we have colleagues in Italy and Portugal. And we'll hear from our colleague here in Finland, from the Finnish Geologic Survey, about what they're doing in Finland. So the Europeans were really the first ones to advance these ideas. But shortly on the heels of the Europeans, the Australians have really embraced this idea, and we have a large number of research groups now in Australia that are actively involved in research in this area. I think probably the largest number of institutions in any one country until very recently has been in Australia. You can see a big mix of national and state institutions, as well as private universities. And there's also research now going on in Korea, at Korea University. And I've been told anecdotally that there are several research groups now working in China, although I don't have the specifics on that. And if others here know much more about what's happening in China, I would be really interested to hear that. And then in the Americas, the first work really started going on actually in Brazil and Colombia, primarily through their state oil companies, Petrobras and Ecopetrol, in collaboration with some local universities, as well as collaborating with European researchers. And here in the US, we were actually very late to the game, I would say. The USGS was the first organization that I'm aware of that started looking at natural hydrogen as a resource. And then we've been joined by the Colorado School of Mines, and then ARPA-E has really catalyzed things with their funding opportunities. And now I think Doug is funding 18 groups to do research around stimulated hydrogen, but they have a number of other programs that they are planning to launch that I think Doug will probably talk about ahead. And I've left Canada off here because Omid is going to tell us about what's happening in Canada. So that's just a very high-level overview of how we've gotten to the state of research around geologic hydrogen today. This is an image from this review article that came out in Science magazine in 2023 that I would recommend that you have a look at if you're not aware of that. This also does a very nice job of giving an overview of what we know about geologic hydrogen. So thank you very much.
And again, next up, Doug Wicks is going to tell us about all that ARPA-E is doing and all the funding opportunities for research in this area.
Yes, and next slide. Okay, so I'm Doug Wicks. I'm with ARPA-E. Been involved with this for a long time. Jeff was one of the people who helped drag me down the rabbit hole that is geologic hydrogen. At ARPA-E, we're focused on the idea of how do we develop the resource. And so I'm going to talk really quickly about some of the work we're doing to stimulate hydrogen production and kind of, open up some eyes about what stimulation might be, as well as talk about some of the engineering aspects of how do we develop hydrogen? How do we move the material out of the subsurface? And I always like to start out with saying, what's our model going to be? And this is a pretty straightforward, simplistic model to say there's different ways we're going to look at hydrogen. We can look at natural hydrogen extraction, where we're going to come down and just find a pocket of hydrogen, drill down to it, put a straw into it, suck it out, and we can use it. The other thing to look at is how do we stimulate the production? So this is coming back and saying we're going to spend an active role, play an active role in actually generating the hydrogen that we bring to the surface. And it's a really very key thing to think about. So we want to be active in this. And there's really reasons to do this. It increases the potential for it and really expands where we can do it. And if we look at this, and I have to say it's quite interesting. One of my colleagues read the slides I have up here last night. And he said I left hydrogen off this slide. But what we need to do it is we're looking at understanding the characteristics, really of how do we control serpentinization. I mean, this is an area that there's good geochemistry that's been studied. It's very much focused around natural earth processes. But are there chances that we can do this differently? So can we look at sustaining the reaction? So what do we need to actually, if this reaction starts going, what do we need to really push this to enable reactive surfaces to increase and going forward? This is more that engineering side. How do we keep fresh surfaces to react with? And then how do we accelerate the reaction speed? And this is quite important, is how do we make it go fast? This is, okay, as what the introduction said, I'm an organic chemist. I do polymers. And actually looking at this as a chemical equation was a great insight for me, because chemistry then says we can catalyze it, we can accelerate it. And there's all types of work that's been done, especially a lot of the work done by NASA, astrobiology, did show there's a whole bunch of ways to catalyze this reaction. And some of the work has been done. Jeff talked about it quickly yesterday in his talk, that the first discussions about it have been done. And so we take this then and say, okay, let's put this into a system. So, how are we going to develop it? Again, we're looking at actually the exploitation of this resource. And it's pretty simple. You drill a well. This is one of those ones I really like. Maybe we come back, we put something in the well to kick it. We want to kick the production going forward with this. By the way, when I showed this slide, the CEO of Halliburton damn near fell out of his chair. He loved that one, and he asked if he could use it. And then we're going to take gas out of the well. It's pretty simple. You know, I go to the oil companies and say, you guys drill wells, you put things down wells, and you take stuff out of wells. Why aren't you doing this? Well, actually, it's really hard. As we've been discussing a lot here today, where do we drill? Into what kind of deposit? What types of wells do we need to do? Do we need to do stimulation wells? Do we just need to stick straws in the ground? So a lot of information has to be looked at. What kind of stimulation are we going to use? Is it going to be mechanical? Is it going to be chemical? Is it going to be biological? I mean, there's biological processes to enhance the rate of hydrogen production. And then getting it out of the ground, do we need to coax it out? What else is going to be coming with it? So how do we pull this out of the ground? Is it going to come out high pressure like the blowout that's shown on top? Or is it going to kind of ooze out of the ground and we have to get creative as engineers to say we can coax it out faster? So this is the focus that we have of our current programs, is really looking at what do we put down the well and how do we begin to get the gas out of it. So if you look at our programs that we have going in, we're looking at saying, how do we drill into these systems and kick the rock in the various ways? Either drilling deep, drilling into active systems and stimulating it. But we are trying to get the geologic processes to make hydrogen down to $1 a kilo or below. And I will be talking tomorrow about the techno-economic analysis we did on this, which will help guide you to say, is this a real objective for what we came up with? So what is stimulation? This is something everybody comes back, you talk to the Europeans and you say stimulation and they're like, oh God, you're going to do hydraulic fracturing. Oh, no way to keep it out. We can't even have a meeting on this. Literally, I couldn't put the word stimulation on an agenda with the French because they're like, somebody might get this. And if they know we're talking about stimulation, but this is really hydraulic fracturing. Very straightforward. Most of the places in the United States, it's easy to do. I fully expect everyone to start practicing this once they find hydrogen to increase the permeability. We can shift the equilibrium. This came from my question last night to Jeff saying, why doesn't the entire subsurface react with all the water that's down there? Why are there things taking place? And it turns out there's an equilibrium, and we have tests being shown now that if you pull the hydrogen out of these deep reservoirs, the reaction rate goes through the roof. Almost everyone has studied serpentinization in closed systems. Yeah, if we're going to be extracting it, it's going to be an open system, and this will stimulate the production of hydrogen, even from a natural occurrence, we think in many cases. Reservoir enrichment we're studying. This is looking at it, saying if we find a system that has 10% hydrogen and 90% nitrogen, for example, and we begin to pull the gas out, are the replenishing gases that are coming in richer in hydrogen? What's going to be the impact of that? Will we see these systems get more and more rich in hydrogen as we pull it out? Because as Jeff has mentioned, hydrogen is really a very promiscuous gas. It's going to react with anything it finds, and it's going to run away if you give it a chance. But if we're actively producing it, it might change that ratios. Could just be low pressure water injection. There are really great ultramafic rocks out there that are dry. It's kind of hard to believe, but I can tell you I've seen them. And it might just be a matter we have to put in low pressure water to feed it to drive it. It could be catalysts and lixiviants. And lixiviant is something that's going to pull something out of the rock intentionally. It turns out many of these catalysts that are being discovered by my teams are already in the rocks. So things like cobalt, nickel, chromium, molybdenum, these all have catalytic effects on the serpentinization reaction. So we did go from a very small interest in geologic hydrogen over the last years. It's amazing, you put money in a dog dish, who shows up? We have a large number of universities. We have some private companies. We have our national labs looking at this. We're paying Argonne to do the life cycle analysis to get it ready for tax credits, which all the commercial companies want to hear about. In total, this geologic hydrogen program, when you take all the subcontractors, is now 23 universities, 7 national labs, and 12 companies involved in this process. 3 years ago, there was Jeff and maybe 1 or 2 other people who knew it might be an energy source. So, aspirations of ARPA-E, everybody asks, well, what are you trying to do? And this is the aspiration slide. Our goals is to get hydrogen at less than $1 a kilo. Low greenhouse gas emissions. This maximizes tax credits for people who want that. And we want hydrogen purities. If you get to 20%, you can use it for a whole bunch of stuff. We want potentials greater than 10 million tons. And the idea is we look at these production rates and the likes, and the idea that this size of deposit will pay for the topside development you have to do. So that said, this is still in its infancy. So ARPA-E is looking at growing a village to say, how do we support this? One of our other programs is we just announced $18 million going into hydrogen detection and quantification. This is looking at leaking and saying, how do we know how much hydrogen is leaking? Directly applicable to what my program is. An H2 Sense is supporting innovative approaches for detection and quantifications across the entire hydrogen supply chain. It's actually funny, people can find leaks, but they can't tell you how much comes out. So Bob Ledoux has done that, has brought in another part of the community into this. And these are all people who are in the back of their mind are thinking geologic hydrogen. So the US community is growing rapidly. The next phase is we have a missing piece of our portfolio. We're looking at stimulation. We're looking at engineering. And as Jeff likes to say, we're not looking at exploration. So we'll be seeing stuff coming out from us in the exploration side. And how do we understand how big the resource is? And we can see this from TEA work, the techno-economic analysis. If we look at the TEA, and we've done in-depth analysis from the discovery all the way through the production of this. And by the way, we're ignoring all the stuff on the surface. Somebody else does all that. My interest stops at the wellhead from this. But it's quite interesting. Our analysis shows that 60% of the capital deployed is before production. So it's that finding the surveys, going through it, doing your exploratory drilling, and analyzing your drilling. That's 60% of the capital to deploy geologic hydrogen. So this is something we have to attack. And again, if you look at this, we're going beyond oil and gas and using techniques. We're trying to develop this to go forward. To say, how do we find this? Simple accumulations are pretty straightforward. The natural gas guys are out there saying, you just pound it with seismic, you get an image back, and maybe you have to adjust your parameters, but you can quantify it fairly well. What happens if it recharges? This is a topic that goes back and forth. Jeff and I have some good discussions on this. He's like, it's slow. I'm like, it's fast. It could be fast, but how do we look at the recharge of these systems? What does that do? Natural gas does not recharge. The models don't have any of that in there. And again, what we're looking for is the assessment of how much is there and how much can be produced over 20 years. Stimulated hydrogen systems, we know nothing. Basically coming back, we have to model these systems and say how much hydrogen can they produce out of these systems to make this economic. And again, I'm sitting there looking at this saying, how do I drive this into the economy? And with that, I'll say I really like Bill Gates's comment about geologic hydrogen. It could be gigantic, but it could be a bust. But if it's really there, wow. And I look forward to questions.
Yeah, that's fine. Thank you. Thank you very much. Next, we're going to hear about research in Canada from Omid Ardakani.
Sure. Thank you very much for the opportunity to present what's happening in Canada. I want to admit that Canada is a little bit behind the US and the rest of the world in this case. And back in 2022, or Director General, because I'm leading the underground hydrogen storage project at Geological Survey of Canada, reached out to me and show me the article by Isabel Moretti that what do you know about natural hydrogen and what's the potential for Canada. From there, I started actually to work on this subject and contacted Jeff, and we technically worked together, and we hope that we can do the assessment of natural hydrogen in North America, US and Canada, unified the prediction. A little bit about Geological Survey of Canada. These are the major priorities of Geological Survey of Canada: geoscience for mineral and northern development, geoscience for land and management, and geoscience for climate and disaster. And we have a geoenergy program that aims to provide geoscience that support the development of emerging energy sources that to achieve the net zero future. This is the technically our program in a nutshell, and as you see here, a geoenergy program have the three major pillar: earth energy storage, which cover under which hydrogen storage is under the program, and emerging new sources that are natural hydrogen and geothermal. A little bit background about natural hydrogen studies and exploration in Canada. Technically, the initial studies back in the 90s in Canadian, Canadian and African Shield started in Canada and published in the Geological Association of Canada, a special paper in 1987. And after that, Professor Barbara Sherwood-Lollar looked at the several mines that some of them actually showed on the Canadian map over there. And they reported the different various the amount of natural hydrogen technically producing within the deep mine in Canadian Shield. The first assessment of the Canada natural hydrogen potential actually happened this year by the Quebec government. Technically, they presented the potential of natural hydrogen, that the evaluation technically stimulated some exploration activity. These are the exploration activities that we are aware. They contacted us for input, probably other companies technically working. QIMC out of Quebec technically started their exploration after report by the government of Quebec. Chapman Petroleum, technically, they started long ago. There was part of the exploration in Mali. The Dennis Bereri, the technically chief exploration of that company, they work on Northern Ontario. Max Power recently bought some land in Saskatchewan, the area that is very active in helium exploration, and finally Northern Hydrogen, looking at hydrogen resources within the Western Canadian Sedimentary Basin. A little bit about what the Quebec researchers has done, the government of Quebec. Technically, they classified their Canadian Shield maps and identified the potential source rock. And technically, the way each criteria, based geological evidence for potential, for example, significant evidence, as you see in that table. And finally, they decided that they suggested that the diversity of this geological environment in Quebec and their wide age range from Archean to Paleozoic make Quebec a promising territory for natural hydrogen exploration. That's the first estimate, the first official assessment in Quebec. But at Geological Survey of Canada, what we did, we have the huge data sets of gas within Canada. Those dark spots, all wells drilled across Canada. We were aware that the gas data is not actually the best way to look at hydrogen, as very well Jeff actually mentioned the reasons in his talks. But we see some anomalies, and anyway, we try to put out a national database, gas database for Canada, and we started actually to look at those possible anomalies over there. This is not the final map. As you see, those dots in Eastern Canada is not added to that one because we are working on unifying the formats of these wells. As you know, oil industry in Eastern Canada is very old. At that time, probably no company measured the hydrogen. If they measured, they don't report it, and we have extracted all those data from published from the PDF file or report and this kind of stuff. And right now, by end of the year, we hope that we unified that data set and published the final map. And the next step was identifying the major reservoirs and source rock in the Canada. Technically, based on the geological map of Canada, we try to classify different type of intrusive, extrusive, green shield, the belts, ophiolite, and this kind of stuff. As you see, the majority of Canada actually covered with exposed Precambrian shield, and 30% of that technically as shown here in this simplified map, modified from Goodwin 1996, covered by the sedimentary cover that would be potential source rock for potential reservoir for Canada. And right now we are using the model or backed on envelope calculation that Barbara Sherwood-Lollar have done for estimation of contribution of Precambrian continental recipient lithosphere to global hydrogen production to update those evaluation for Canada and find out, because in this paper, they technically use the average, the composition of the continental crust, Precambrian continental crust. We're trying actually to use Canadian example and accurate measurement over there. Another activity that right now we are doing, Western Canadian Sedimentary Basin, largest basin, we use all the published data and trying actually to complete the coverage of the Precambrian shield, technically the analysis for uranium, thorium, and potassium to not only produce a heat map over the Western Canadian Sedimentary Basin, also hydrogen and helium production rate in that area. These are the activities that we are doing, and eventually, as I mentioned, after Jeff, we have a discussion since he has started on his fantastic model. We are trying, when the model published, apply this whole model based on the North America and have a unified assessment of natural hydrogen resources within Canada. Because technically all the resources for this is ready. We already have a trilateral collaboration between GSE, USGS, and Geoscience Australia on critical mineral mapping initiative. That's one of the targets is to provide to produce the unified map of North America, and this would be a very good actually starting point to apply what Jeff is going to do to apply to the Canadian as well. In summary, as we discussed since yesterday, this field of geoscience, energy geoscience is frontier. A lot of new development happening every day. And as you know, there are significant uncertainties about hydrogen origin, natural hydrogen migration, and accumulation mechanism. The goal at Geological Survey of Canada, a federal research agency, is that to generating the basic data and estimate of Canada natural hydrogen resources potential to inform public decision maker and industry for further use, for further exploration and advancement in this field. Thank you so much for your attention.
Good job. And our final talk in this session is by Teppo Arola. He's going to talk about research in Finland.
Okay, my name is Teppo Arola. Thank you for giving this opportunity to come to talk. I come from the Geological Survey of Finland. And once we get this, yes. So let's start. Finland is situated in North Europe. You know, there's a northern and western country neighbors are Norway and Sweden. There's Estonia and south, and then we share a same red devil neighbor as you do in Alaska. So there's our capital, which is Helsinki, and I'm living in Turku, which is also the coolest city of the country. And the Arctic Circle is cutting the country so that approximately 1/3 of the country is north from Arctic Circle, Arctic Circle, and 2/3 of is south from Arctic Circle. We are having GTK Geologic Group, and there's 2 main research questions which is in our strategy. And one is in geothermal system, and the second one is for natural hydrogen. So this is quite high level in our organization. But yeah. So believe it not, we have found the hydrogen in Finland in our Fennoscandian crystalline basement. However, all the measurements what have been done has not aimed for hydrogen research. There are several other things, and that's why this current database includes different data, different from several drill holes, different sampling methods, and so on. But as you can see, the northern part, which we call Lapland, is unexplored area. And here we have a volumetric concentration of hydrogen. So it's a concentration of hydrogen in gas phase in water. Then we have some places where we have measured water gas ratio, which make it possible to have this milliliter per liter of water, and so give kind of a right concentration. And here in the map, you can basically divide the yellowish country, yellowish colors present the Archean basement, and the other one presents Proterozoic. And if we see the numbers and top five hydrogen foundings, we can find first is the Outokumpu. Well, there's a black schist serpentinite. Then Pyhäsalmi is a mine also with the similar rocks. And those samples have been taken quite deep. And then there's a source on the right-hand side. Then we have these Ylistarovan and Olkiluoto, which are basically gneisses and schist. And finally, we have Pori, which is a sandstone. So we really don't know why there's a hydrogen in our sandstone. And that makes this interesting. We know that there's some Mafic dikes cutting the sandstone, but not in the place where the sample has been taken. Then we published this map on the right-hand side of the slide. We put this possible potential rock on a map. And there are, like you can see, there's ultramafic, layered intrusions, ophiolites, serpentinized greenstone. And then there's this Rapakvi granites, which are possible for radiolysis. And we have got a lot of lithological data. So that is not a problem. There's a lot of mining activities on these ultramafic areas, and that's why we have a lot of data available. Then when it comes for radiolysis, there's a clear correlation of heat production, naturally because it's a radiogenic heat productive also. So I think we should include for our possible potential rock max this central Lapland granitoid area also. It's missing now. But there's of course a real correlation between heat flow and potential. So what shall we do in next? And when it's in our strategy, so we have a plan. Of course, we need more data. We need more basic data. We need to take samples. We need to understand why there's somewhere you can find a hydrogen and some places you don't. So it's in a basic research stage. Of course, we have to look for this enhanced hydrogen generation. Then we have to develop these techniques because the gas in our ground is not pure hydrogen. It's a mix of there's methane, helium, argon, neon, a lot of gas. So what would be the best way to technically separate it? And then in our country, there is no current legislation ready for natural hydrogen research. So we have to find out that issue also. And here are some photos. The right hand, there's our sampling equipment, and then do some sampling on a field. Yeah, well, I can take this. Yes, and of course, these three first things gives the economy of hydrogen research. But at the current world situation, I've been asking, what is the reasonable price for your own produced energy? You know, if there's if there's a war in neighbor countries and those energy markets are kind of you know, mixing and everything is upside down. So even so, we are not looking for that. Should it be under $1 or $2, basically? Then I put some things to talk about the Arctic environment. What does it mean in natural hydrogen? Of course, we know that in top ground here in these areas, everything happens more slower than in warm areas. One issue is that could permafrost or frost or these post-glacial clays, could they form a seal or trap in the areas when there's no seal or trap in a bedrock? And for example, we have large geological lineaments situated under the thick section of post-glacial clays. Then the third one is kind of a wild idea. We know that this anthropogenic heat flow causes a problem, geotechnical environmental problem in this region. You know, this building is leaking heat to the ground. But we have a solution for that, and it's geothermal. Could we combine this geothermal and natural hydrogen and helium? This is just a wild idea. But the next one is not a wild idea. Everyone who has been on a field in these environments knows that it's not a straightforward. So we have to develop the sampling methods and analytical tools for Arctic region also. You know, in winter it's dark and cold, and summer there's millions of mosquitoes, if nothing else. I think that was all I say. So kiitos. Thank you.
Thank you very much. So now we're going to answer some questions. If there are questions from the audience, please raise your hand or put them in the Slido. We'll pull them up. I guess while we're waiting this to happen, I was going to ask the panel, if you were going to write a proposal, your next proposal, what's it for? Instrumentation, modeling, sampling techniques, theory, what?
Yes.
And if you were going to request proposals, what's the highest priority? Let me just.
The highest priorities would be to take a look at our RFI that should come out in the next week, and you'll see what we're thinking about. And it's going to be modeling and analytical techniques is the next big challenge.
So I would just add that I've been promoting this idea that Senator Murkowski referred to in her opening remarks, that I think we need a major collaborative international program, something comparable to what's been done for gas hydrates. One of the challenges I see is that we have people that are out there collecting data, but it's scattered and it's not coherent, and there's not enough sharing of data, and we need a lot of really good subsurface data, and we need to be drilling wells and collecting data from wells, and that's a big expensive program that's not going to be taken on by any single institution, and it needs to be coordinated and brought all together. So that's what I would really like to see happen.
Well, yeah, it's kind of, first I think what is needed is kind of a roadmap how to go forward, because there's so much things which are so interesting thing, and you got, you know, where should I go? What direction? And that's one issue, to make a good plan to go further.
Yeah, I think one of the best the approaches that shown it's the productive, it's a trilateral for the critical minerals that, for example, USGS, GSC, and Geoscience Australia have done. They created a lot of databases, international databases, unified databases. This exercise can be actually expanded to Europe and other areas that are active in study and exploration of natural hydrogen.
Okay, any questions from the room? Not seeing any, we'll go to Slido. Please.
I look at it and want to go back to the enhanced geothermal guys and say porosity enhancement.
Thanks. Any other questions from the floor? Please. Yeah, the question was, do we know anything about Russian research in this area, or do we know of any collaborations? Any answers from the panel, from the room?
There are a lot of Russians and Ukrainians running around the world, not in Russia, trying to develop resources. So I think they're all running away. I have not come across a group that's thinking about it at all.
Yeah, I would just add that, yeah, it's a bit ironic because the former Soviet Union was very big on natural hydrogen, but as far as I know, there's nothing actively going on today in Russia, but in Ukraine and other parts, other former Soviet states, there's a big interest. So yeah.
Yeah, I agree with Jeff says. The basic data is there and it's very high quality data. But at the current situation, none of us should, cooperate with them.
Mark.
Yeah, so from what I understand, it doesn't exist, and we do need it absolutely. And the service companies are working on it. I know that like the SLBs and Halliburton are working on their own techniques and everything, but it's not standardized yet, and that's very critical. And so I think a group like SPE needs to be involved and develop standards for this. And probably there's not enough of a market quite yet that it hasn't gotten traction yet, but once we get a few more wells, if we get that one big discovery, then this is going to come on very quickly, I think. Yeah.
Thanks. Yeah.
For Canada, there's obviously a very large iron mine in Baffin Island, the Mary River Project. I don't know about Finland, but I'm familiar with the very large Kirkenes iron mine, and also one in Sweden. Hitler needed very quickly. Is there any work going on in your countries of working with iron-rich rock or tailings?
Currently in Canada, no. Because volumetrically banded iron formation in Canada is not actually a huge source. But no, I'm not aware of any company actually interested in the working on the banded iron formation iron mines for the hydrogen generation. What we are doing, I didn't actually mention because map was not ready. We have a lot of uranium mine. We technically map those uranium mines to find out if the high concentration of uranium into those uranium mines cause some kind of radiolysis, water radiolysis in those the strata around those mines or not, as well as kimberlite. I forgot actually to mention, we also map those kimberlite because we have probably these are all conceptual models. For finding diamond, hydrogen was a proxy technically. And right now, all of those diamond mines, for example, in Arctic region, that small communities working over there is closing down. And we are looking at those mines, for example, for a small production of hydrogen, probably in those areas. These are the things that our next step plan that if we get funding, we are looking at those resources in the Canada.
So the time's up for this panel, but I'd like to ask the panelists, any of those questions on the Slido screen you're interested or burning desire to answer? If so,
I'll start out with the first one. Yes, you can frack hard rocks. I mean, a lot of this technology was developed for enhanced geothermal systems, so it's a well-known process, and there's further developments. Technology is moving very, very fast in this area. So I don't see mechanical fracking of a rock. We got somebody here who's bad to the bone, so we got to be careful of him. All right.
anything else from the panel? Okay, thank you very much. I'd like to give them another round of applause. Excellent panel.
Okay, testing the microphone. All right, well, it's lunch break is now over. It's time to go back to work. So if I can encourage you to return to your assigned tables, that would be fantastic. And yes, if we could have Barbara come up and the speakers for this next session, that's going to be very helpful. So our first session this afternoon is an extension of hydrogen research that's being conducted. And this is, we're talking about hydrogen research that's being conducted in the United States now. And this is just a snapshot of the work that's going on. When we were putting this program together and struggling to fill our session on the cryosphere and hydrogen, we started uncovering more and more research activities that were going on both domestically in the United States, but around the world as well. And it rapidly became apparent that we could fill a multi-day session just with the research activities that are being conducted very easily. And so this is just a very small snapshot. We have, I think we have 4 presenters this afternoon talking about different research that's happening domestically. And our moderator, we're very happy to have with us, is Barbara Ransom. Dr. Ransom is a UC Berkeley graduate in theoretical geochemistry, so she's right at home here. She's a 20-year veteran of the National Science Foundation, and she's in the Directorate for Geosciences. And Barbara's a great person to talk to if you have ideas about science that you want to do or science that you want to get funded. So it's fantastic to have her here. She has a broad background in earth and ocean sciences and has spent time overseas in South Africa, France, Switzerland, and the UK. And at the National Science Foundation, she has built a portfolio of industry university cooperative research centers known as IUCRCs, which is something that I became familiar with recently. And those bring teams from universities together with industry to address the needs and questions of industry in a particular sector. And she's also a catalyst for working with other government agencies like DOE, the Air Force, and NIH. And very happy to have Barbara here with us today. So thank you, Barbara.
All right. It's a pleasure to be here. I am like super psyched about this whole meeting. I'm learning a lot of things that I didn't know about, but should know about and will know about by the time we're done here. And what I'm doing is I am going to be holding the session today, which is, let's see, what's the title of it? Okay. The title is Geological Hydrogen Research number 2. And I know that there have been a lot of questions out here, and I was just talking to some of my colleagues at the table, and after every one of these panels, we have the same questions all the time. And what I'm thinking is that this panel is going to be different for you, because now we're going to talk about the real stuff. We're no longer talking about the speculation. We're going to be talking about what are the properties of these reservoirs, these resource rocks, and how do you know what it is? So this panel is going to start to reveal to you some of the tools and things that we can actually use to know what's going on in the subsurface so that we can actually decide whether we should be going to various plays or not to various plays. So I have 4 esteemed panelists here, and I want to just give you a little bit of a introduction. I'll do that as each one comes to make their presentation. I'll tell you a little about who they are. But I've got Shuvajit, who is Bhattacharya from UT Texas, and he'll be coming online. He's going to be participating with us virtually today. I've got Yaoguo Li from Colorado School of Mines. I have Dr. Todi Larson from the University of Texas Bureau of Economic Geology. And then I also have Mengli Zhang from Colorado School of Mines. And these are all experts in the area of what's going on in the subsurface and how do you characterize that? What are its physical properties? How do you know what's happening down there and like what it looks like? So all the things that we've been talking about here with regard to transport in the subsurface, or maybe you got to do some kind of fracking down there, or what is it that you have to do down there? How do you find out where its manifestation is, and maybe how we can get some of this hydrogen out of the ground? So why don't we start with Dr. Shuvajit. He's from University of Texas at Austin and is also at the Bureau of Economic Geology. He's going to talk to you right now about geophysics methods for exploring geologic and stimulated hydrogen. I'd like to just give you an idea of where he's been in the past. He was previously affiliated actually here in Alaska at Anchorage, and has also worked for Battelle. He's a petrophysicist and a geophysicist. He works on unconventional energy resources such as hydrogen storage, which is something we care about here, geothermal, carbon storage, and he's got strengths in new concepts and workflows in 3D seismic, which is actually pretty awesome. If you've never seen a 3D seismic section, it is really like a cube, really super cool. And he does petrophysical analysis of subsurface characterization and monitoring. He's got numerous peer-reviewed publications and is actually the author of 2 books and has innumerable conferences and abstracts on petrophysics and its analysis. He's also worked on formation evaluations, quantitative 3D seismic interpretation, and this includes seismic attributes and inversion modeling, machine learning, and also integrated subsurface characterization. So, Dr. Bhattacharya, are you there online?
Yes, thanks for the nice introduction. If you can hear me.
Yes, we can. Go ahead.
Thank you very much for that introduction. And Franek, whoever said that don't study mud rocks in Michigan, we got to hunt that person down. Yeah, so I'm a geologist, geochemist. I guess the only geochemist up here with quite a few geophysicists. I do a lot in the unconventional oil and gas. And so the bulk of my work that's not hydrogen related is trying to characterize subsurface reservoirs. What I've heard throughout this this meeting is this question of, what are these reservoirs going to look like? And are there analogies to conventional reservoirs, oil and gas, unconventional reservoirs with oil and gas? I'll introduce some concepts along that and also talk about some of the geochemistry that I think is going to control hydrogen transport and hydrogen storage in these subsurface reservoirs. And then I'll give some examples from Kansas. So back to Kansas. I actually called Franek when I found out he was coming here because I hate to come to be the Texan coming to Alaska to talk about Kansas, but here we go. Next slide. Oh, does it get advanced up here? Okay. Oh, I see. Oh boy. Okay, here we go. Scaling is key. I think this is, if we've learned anything in oil and gas, is that the sooner we define what the reservoir looks like or what we think it's going to look like, and the sooner we try to integrate across the multiple scales, the sooner we're going to get to the answer of understanding, how we're going to tap this resource. And so this is sort of how I see it. With ARPA-E, we're doing a lot of work on the left side of this. We're doing a lot of benchtop experiments. And so we're really diving into the chemistry to understand how we can stimulate these iron-bearing rocks to produce more iron than they currently are. Kind of think of them as underperforming systems. We know they can generate hydrogen. What can we do to kick more hydrogen out of that? And then go all the way over to the right, and I think that's where we're going, or where we need to be going, which is on the resource assessment. So how can we characterize these reservoirs? How can we guess where these reservoirs are going to be? And what tools can we use to really, estimate what's the resource potential of these? And in the middle, there's the joke that geologists aren't scientists. Well, we're cartoon artists at best. And so you need a model, some sort of cartoon model to sort of describe, how or what you think the subsurface looks like. And so this one, I sort of modified it. I basically took it from Hytera's model of the Mid-Continent in Kansas and the Nemaha Ridge, and then added a few additional things on here. The one thing I added is, you see the yellow gas pockets up in the Paleozoic strata. I want to include into the conversation not only oil and gas deposits, but helium deposits. I think that's the other type of deposit we got to start thinking about. We've made some analogs to helium to hydrogen, but let's talk a little bit about what helium deposits actually look like, because they're very different than oil and gas deposits, and think maybe that's another analog we have to consider. So no outline, just questions, because I think that's where we are in the science here. These are sort of what I put down and I have in the back of my head of like, these are what I think we need to ask the important questions here. And what's nice to see is that they overlap with a lot of questions we've been asking here. The rate of geologic hydrogen accumulation or production. We obviously need to know that to understand if this thing is actually recharging at quick time frames or long time frames, which is one of the points that Doug was making earlier today. Age of geologic hydrogen. We can't date the hydrogen, but we can start to build up some conceptual models of when that hydrogen was actually formed, and really get to that question of, is it recent charging or is it accumulated over time? And is it accumulated over long times? I think the third bullet, what type of reservoir is it and what is it analogous to? Is it conventional? And if it's a conventional reservoir, then by definition, you essentially have transport and storage. So there has to be transport of hydrogen over distances and then stored into a high porosity reservoir. Or is it unconventional? And unconventional in oil and gas is essentially it's self-charging. The source rock is the reservoir. And that's what distinguishes unconventional from conventional. We may rephrase what exactly self-sourcing is in the hydrogen world. Or is it hybrid? Are we looking at a basement play? Are we looking at stratigraphic traps? Those are going to be two very different systems. And I think we should really think clearly about that. And then also relationships between helium and hydrogen resources. We've already been talking that a little bit. There's some similarities and there's some key differences. Obviously with economics, if you can get both, you're better off. And then approaches to engineer the subsurface hydrogen production, and that's the focus of our ARPA-E project. I'm not a geophysicist, I'm a geochemist, but I'm really glad I put a magnetic susceptibility map, realizing there'd be other geophysicists up here. I use this as a frame of reference. Kansas, you can see outlined, that's what the rest of this talk is gonna go and talk about, or we're gonna focus on. We're doing work up in the Duluth complex. We're doing work off the map up in Ontario. What I put here though is just sort of the main areas that I'm seeing sort of hitting the news these days in North America, where either hydrogen exploration is being looked at or helium exploration is being looked at. And so you got the Kevin Dome up in Montana, helium, potentially hydrogen. The Duluth complex, helium, potentially hydrogen. Obviously the Nemaha Ridge, Kansas, all hydrogen right now. And then going to Arizona is the McCoy field, which is helium, but now we're starting to look at hydrogen there. The reason for the magnetic susceptibility map is that that's basically one of our views of basement. And it ties to magnetic susceptibility, ties to iron, magnetite. And so essentially what we're going to be looking for is characterizing how much iron is in the subsurface. Just one of the tools we have to our availability. Nothing makes Kansas look more spectacular than a magnetic susceptibility map. So here's the magnetic susceptibility map of Kansas. And what I've done is we basically scraped everything we could find with scout tickets for who's getting leases and drilling wells in Kansas. And so Hytera was easy to find. Coloma's a little bit more difficult, but we put up as many of the wells that we could that are publicly available to see kind of where they're landing. And what you can see in the Mid-Continental Rift is to the left a little bit. It's a big pink area coming down just about the middle. That big white line coming up from north to south over on the east side of it. It's a big fault system that's off to the east of the Nemaha Ridge. Here's a cross section down on the bottom from Burberry et al. 2014. And what that's showing is that you can see the Mid-Con Rift, that sort of syncline sort of in the middle of the map, and then the Nemaha Ridge just sticks up. The bulk of the wells that are being drilled right now for exploration for hydrogen are on the Nemaha Ridge and distant, by tens of kilometers from the Mid-Continental Rift. That was, kind of the first surprise that I got from this, doing this. What we're going to focus on here is the Sudarosh Well 2. That was, there's a publication from 2017. Julia Gillard worked with David Newell over at Kansas. And I think there's a lot of lessons to be learned from the data from that well. Before we get to that, here's the cross section. And this just, this is really taken from Hytera, but I do add in what the helium sort of reservoirs look like that are typical of sort of the Western United States. But essentially what you're looking at with the cross section across Kansas here is you can see the Nemaha Ridge. We're going to talk about the Sudarosh number 2 well. There's a Sudarosh number 3 that's been drilled just about a half kilometer away from that. So it's a really good proxy to think about, what's going on with hydrogen. You can see where the metasediments are. Those are the Proterozoic metasediments within the Mid-Con Rift. That's going to be a source of hydrogen from serpentinization. It's also going to be a source of helium, from helium or uranium thorium decay. And so there's multiple sources both of noble gases and for hydrogen. And then there's a lot of faulting. And I think really what they're probably tapping right now on the Nemaha Ridge is the deep-seated faults that are providing a conduit from basement up to the shallow surfaces. I think there's some questions that I don't really know why they're targeting the shallower wells. I can come up with some ideas for that, rather than maybe the deeper wells in the Mid-Continental Rift. And then another thing I want to point out with helium, the model for helium accumulation is essentially helium gets trapped in groundwater. It gets transported long distances. And then there's a exsolution dissolution that happens in gas pockets. So if you look at helium deposits we find throughout Kansas and in the panhandle of Texas, natural gas pockets, CO2 gas pockets, nitrogen gas pockets. And so it's a very different type of process of accumulation for noble gases than we find for, we think we're going to find for hydrogen. I think that's going to be really important. Okay, this is the work of Gillard from 2017, and they really did some good work. And this well, to my knowledge, is the one that really put Kansas on the map. And you can see the date on the x-axis going from 2008 all the way through 2014. And there's 2 different y-axes. One of them is hydrogen and nitrogen shown on the left, and then it's helium and methane shown on the right. And obviously that very first well, when they hit it in 2008, that was the 90% hydrogen. That put this on the map. They shut the well in and they plugged it, and you can see the plug where the well was drilled into the fractured basement, and it was when it got drilled into the fractured basement, that's when that 90% hydrogen hit. After that, they plugged it, and then it's been it's basically an artesian well. So it's an aquifer well that's tapping Paleozoic strata, Mississippian, I believe, or no, late Pennsylvanian strata. And so all the sampling that's been happening at the Sudarosh well from 2011 onward is not when it's tapped into the basement. Am I? Yeah, yeah. I can end on this one right here.
We got one more. You
Yeah, one more. So the point here is that fractured basement, access to fractured basement is really important for hydrogen. And then when you lose that direct access to the fractured basement, that's when I think you're going to struggle with finding elevated hydrogen. So my take home from this one is take this one pretty seriously, but understand the importance of access to fractured basement.
All right, as you can see, geophysics is going to be one of the keys for us to be able to see into the subsurface and actually get a handle on what could actually be a useful reservoir and what kind of properties you're going to have there that you can already expect without having to punch a hole in the ground to like try to do it just sort of as a wildcatter. So anyway, we're going to pull up the Slido and do a couple of questions. We don't have a whole lot of time here, but let's see. Why don't my panelists and Dr. Bhattacharya, are you still there? I can't tell. Anyway, okay, I'll tell you what. What I guess I'm going to ask this of the panelists, what's a major challenge in applying geophysics to geological hydrogen exploration? If you could just pass this among yourselves, that would be great. And just a brief answer.
I would say at the moment, the biggest challenge is establishing the physical properties, namely the velocity, density, susceptibility, etc., associated with the hydrogen generation products. That's something actually needs a lot of work.
I'm not a geophysicist.
Yeah, I think the biggest challenge is we need to build new geophysical interpretations. It's different from the hydrocarbon system, different from the mineral system. So what's the new interpretation method for the suitable for the geologic hydrogen? That's a big challenge.
Okay, I'd like to know something since we have some companies here. What do you see as the potential for academics to partner more closely with the private sector in this whole area of exploration and, that all of you are doing? And what would you see there? Okay, Dr. Lee.
Sorry, I was taking notes. And the industry academic collaboration. I think that's really the key. The thing is that academics only have very limited access to the real data, a real situation. And you look at the history of university research on exploration, the best result came out of industry-driven. So it's almost market pull. So that's where the interaction comes, identify a problem, then the research, collaborative research provides some solution to push paths forward.
Data sharing and funding students. Funding students, a master's student's a 2-year program, and that gives us a really good indication that they're in it. And so that helps out a lot, and students are amazing for doing the work. And then the data sharing is pretty tricky. And so anything that would foster data sharing, from industry to academic is huge.
Yeah, I think finding students is important. We always need the new blood, the innovative ideas from students, and also for the data sharing. Yeah, we hope we can have more data sharing from the industry. There is a balance between data sharing and the property of industry.
Okay, great. And I think we're right on time now. And actually, our esteemed panelists, I believe their contact information is in the handouts. They have information on how to contact these people. Well, you know their name, you can Google them. And they'd be happy to answer any questions that you might have on the geophysics. How do you image into the subsurface so you can really get a better handle on the characterizations of the source rock, of the, traps, of whatever you might have there. So anyway, I want to thank our panelists. If you'd please give them a hand for their time here, that'd be great. And let me turn this back over to Barb.
Okay, I'll let you guys go. What's the best way that Alaskan research can contribute to the global effort?
We had using the core sample library and water wells to start to get indication of mafic rock hydrogen generation potential and current seeps.
Thank you. Okay, next table. You're next.
See, I think our best idea was that Alaska just has a lot of expertise and knowledge to transfer to the community. And when you think about like the division of geology and geophysical surveys and whatnot, and just their capability, their ability to go out and do, just collect samples and provide data. I think that's one of our biggest advantages here.
Okay, you sure you mark it? Circle it or something. All right, how about this table, 11? Best idea.
I think that we zeroed in on the best idea has to do with with policy developments because Alaska is ahead. We've been in the oil and gas industry for many, many years, very dependent on it. A lot of policies have been developed specifically about rights to oil and gas or minerals. And then here's hydrogen. We haven't figured that out, and we should, or you're not going to get companies investing in something they don't have the right to.
Thank you. All right, this table. What's your best idea?
Our best idea is just fostering more public research so the data is actually publicly accessible for the rest of the world, as opposed to being funded mostly by private industries and private data.
Right. Circle that one. Okay. This table, table 9.
We talked about several ideas, but it was pretty clear that given the immensity of the size of the state, offshore and onshore, and the incredible variety of geologic regimes, some fundamental research in geophysical survey methods could potentially have beneficial globally. So doing geophysical survey method fundamental research is our best recommendation.
The last two tables stole our ideas. Okay, the next best idea is permitting processes need to be adapted and streamlined for projects to progress.
Thank you. This table.
You picked it.
Is it marked?
This
one. Circle it or something.
All right. Best idea. Alaska has reduced crust with multiple geologic systems, ideal for, what is it? Mass triangulations? Multi-analysis.
Write it so I can read it. Circle it. Thank you. Did you?
We have a lot of expertise in geological studies, geophysical studies, geological materials, and in the state, we are the experts in doing research in challenging environments. And I just want to put in a plug, not only for DGGS here, but also the university. We have long-standing expertise in doing geological and geophysical studies in the Arctic and in very challenging conditions. And I feel like that's something that we can really use to tackle this problem and provide some really good results from publicly funded research, which is publicly available. And we can also export that expertise to other Arctic regions who are also interested in this area.
Thank you. You're the sole person at this table. What's your best idea?
Well, that means I have no competition. I think our question is, we've heard lots and lots about geology and generation and storage and so on in the natural setting. What are the engineering challenges associated with hydrogen if different from oil and gas? I'm an engineer, so I want to know.
Write it on a sticky. Okay, table 4. What's your best idea?
Our best idea was Alaska has unique geology with a significant
that can significantly contribute to the understanding of the serpentinization process and tectonic role in hydrogen science.
Circle it. Thank you. All right, table 3. What's your best idea?
We had a couple ideas. Locally in the Geophysical Institute, we have a large number of researchers in fields like volcanology, seismology, permafrost, and critical minerals, who we're trying to get. We need to get educated to address this problem. And also, we have a pretty large drone program, and most of our researchers use drones already all around Alaska. So we got to figure out ways to exploit unmanned aircraft for these this research.
Thank you. Good to know, huh? All right, table 2.
So to be honest, we thought we were answering the question about what should policymakers know about hydrogen and how to produce it here in Alaska. Nevertheless, all of our sticky notes are actually relevant to this question. And the one that I will highlight is that the most important one that we think is leveraging both international contacts and, similar to what you said, internal contacts here in Alaska. Lots of expertise on the natural geology here, but lots of international expertise on hydrogen. So we want to leverage those together.
All right, last but not least, table 1. What's your thing?
Okay. Well, by the very end here, what's original? So what we had was really understanding the interaction of hydrogen in the cryosphere, and then also abundant and diverse geology applicable to global efforts.
Some similarities, some differences. Would somebody from each table take your flip chart and put it on the wall over here? I think this is our biggest open space. Take a break. We'll see you back at the end of the break time, which is...
All right, everybody, if I could have you take your seats again. We're about to start our last session of the day. Well, our last panel session, or maybe our last, whatever. Session 8, we're starting session 8. So, this session is kind of stepping beyond the work that has been done and is being done, and is starting to look into, what could the potential impacts be on Alaska if geologic hydrogen is a viable resource? What difference could that make for our state? And then in the future sessions, we'll start to morph that into policy and regulation discussions, and also talk about some of the projects that are ongoing here in the state. So our moderator for this session is Dr. Lance Miller. And Lance is a well-known fixture in Alaska. Well, fixture, make him sound like a piece of furniture here. But he's a feature of geoscience in Alaska. And he started his background with a BS at Stanford, a master's in economic geology from the University of Alaska Fairbanks, and then got his PhD in economic and structural geology from the University of Arizona. He's had a long history in the mining industry in North America, Mexico, Canada, US Arctic, Asia, Russia, Africa. So he's a well-traveled, well-versed economic geologist. He's also no slouch when it comes to participating in organizations. I'm going to cut this off. He sent me this thing. It's like 50 pages long, but he is let me just get into this. He's current president of the Resource Development Council, member of the Council of Alaska Producers, past chairman of the Alaska Minerals Commission, University of Alaska Anchorage Geoscience Community Advisory Board. He's the chair of our Critical Mineral Collaborative. And on top of that, he's the vice president of natural resources for Nana Regional Corporation here in Alaska. So, and before I get started, I learned a piece of trivia about Lance that before he went to Stanford to do his PhD, he had a stint as a driller. So, yeah, a driller. We got a driller up here on stage, so we can ask all our drilling questions to Lance.
Thanks, Steve. Yeah, it's actually, I learned from somebody, it's good to have a trade. And I did drill for several years as a helper and then a driller. And it turned out, you know, people said, oh, you should go and do geology and be a field assistant. But it turned out being a driller was one of the best things, because my first project was about a 300,000 foot drilling program. And then I could go and talk to the contractor and they knew I drilled. So there you go. And I can always go back and do that again. Not really. So thanks. We have a great panel here. And I thought to frame it a little bit, I was thinking about this and sort of characterize what I've heard to date as sort of limitless optimism sprinkled with skeptical pragmatism. And I've been more on the maybe skeptic side, but it's been really fun to listen to and think again about geology and science and chemistry. And I think there is a lot of opportunity. And that's where I think this session we're sort of transferring a little, or phase shift, is let's sort of assume that we maybe found something. Because our questions for the panelists, just to get out there, what do you, is in your agenda, what do you think is a potential future relevance of geologic hydrogen in Alaska? And what can your agency do or not do about advancing research and exploration? So that really does assume in this optimism that we have something that we could use somewhere. And I think we all agree it's part of the mix. Hydrogen will be part of the mix regardless. I'll just do a quick introduction of each one of the panelists briefly. And I know you can go to LinkedIn and things like that. But first, for Erin Whitney, Dr. Whitney is the director of the Arctic Energy Office. In this role, she leads the Arctic Energy Office mission to bring the Arctic to the U.S. Department of Energy and DOE to Alaska. She is based in Anchorage and works with Arctic stakeholders in innovative ways to meet the energy, science, and national security needs of the United States and its allies. She previously worked at ACEP and was also a scientist at DOE's NREL lab in Colorado. She has a bachelor's degree in chemistry from Williams College in Massachusetts. She's also a skier, and it seems like a lot of skiers go to Williams, and a PhD in physical chemistry from the University of Colorado at Boulder. And other fun facts, I think I first met Erin in the mid-90s when she was on the Juneau Icefield Research Program in Southeast Alaska. And I was involved with that from a young lad myself. Next is, I'd like to introduce Dr. Hartman. He is Chief Innovation Officer with the U.S. Air Force Office of Energy Assurance. He is responsible for energy security initiatives for the Air and Space Force. As CINO, he identifies and develops strategies to deploy innovative solutions to enhance energy resilience worldwide with global partners in academia, industry, and government. He holds a PhD in policy and management and has held adjunct faculty positions at George Washington University and Georgetown University, and a board member of several private and public sector boards. He also advises startups in companies and has helped with spin-outs as well. And then finally, today here with us is John Boyle. He is a commissioner of Alaska's Department of Natural Resources since about 2023. He previously clerked in the Alaska court system here in Fairbanks, lived in Yaoguo to serve in the North Slope borough government, and has worked in the oil and gas industry as well. So he has a breadth of industry, private sector, and public sector experience. John Boyle leads 1,200 DNR employees from across the state in the department's mission to develop, conserve, and maximize the use of Alaska's natural resources consistent with public interest. And also John Crowther is here, and Brent Goodrum in the department. So if you have other questions for DNR as well.
Hard questions.
The hard questions go to them. Yeah. So I think with that, we're going to kind of go down, Erin, Richard, John, and then we'll sort of do the Q and have that party. Yep.
All right. Thank you very much, Lance.
I'm Erin. I'm from the Arctic Energy Office at the U.S. Department of Energy, and we're going to sort of move up to 35,000 feet here as we think about, and I think the instructions were the relevance of geologic hydrogen to Alaska, and then what my agency or our agency, I'm here from the Department of Energy along with Doug Wicks, also from ARPA-E, can do to move the research forward. And I have to say that, you know, as I've been listening to these talks and in the very technical details, I got a little discouraged and I thought, oh, you know, this is not such a technically detailed talk. But it also occurs to me that there's a lot of people from here who are not from Alaska, who may not understand how hydrogen fits into the opportunities in Alaska, and specifically the opportunities in Alaska in the context of the world. So please bear with me if you've heard some of this before, but I hope for some of you, maybe it gives you some insight into why hydrogen really could be important for Alaska. And the other thing I want to underscore here that we were talking about at our table this morning is that you know, we're not going to achieve this energy transition and this decarbonization with our existing sources of energy. Like we need something like hydrogen. We need an additional boost in the arm to achieve this decarbonization globally and to achieve this energy transition. And I think that's one of the reasons geologic hydrogen is so compelling. It really is perhaps the key or one of the keys to completing this transition. So without further ado, let's go ahead and move forward. I think I actually have to do that. Gosh, wrong button. There we go. The Arctic Energy Office is one of about 60 offices within the Department of Energy. ARPA-E is another office that Doug is here representing. We are the only regional office within the Department of Energy ecosystem. And as Lance mentioned, I'm based in Anchorage. I'm an Alaska kid. I grew up here and then left for 20 some odd years to start my career, and finally came back here with a husband and a couple kids. And it's a real privilege to be working on behalf of the Arctic in my home state on interesting Arctic solutions. Our mission is to provide the connective tissue between the Department of Energy and the Arctic. So we're a convening body. We facilitate, we connect, we make sure that the Arctic is at the table and that the department is coordinating its Arctic activities and has a cohesive plan for the Arctic. So we do lots more than just hydrogen. We are involved and have an awareness of lots of different technology areas. And then we also help create awareness around or among our national lab partners as well. So this is important because you know, as an Alaskan myself, I want to see the Arctic at the table, you know, if not leading the energy transition. And then we also have some big equities up here. You know, we have nearly half of the nation's federally recognized tribes. And so this is an important region. And to some extent, you know, we're not as well understood up here by our counterparts in Washington, D.C. So we help to be sort of that translating entity. Let's see here. Our team is small but mighty. There's a couple of us here in Alaska. Two of my colleagues are here, Paul and Lisa. Raise your hands, Paul and Lisa. And then we've got a couple folks on the East Coast, and we have a gentleman, one of our senior energy advisors, Levi Kilcher, in Colorado. We have a variety of expertise. And as I'm thinking about what, you know, our agency and what our office, which is very, very small, the smallest office at DOE, can do to move this forward, you know, one of the things that comes to mind is the technology fellows we can bring to bear. So for example, Paul and Lisa are technology fellows in our office. Paul is a hydrogen fellow who is jointly supported by the university and our office. And then Lisa is supported by our nuclear energy office and works as our nuclear energy advisor in the Arctic Energy Office. And as I've been listening to these conversations, it strikes me that perhaps there could be a joint effort around geologic hydrogen in this vein, where, you know, the Arctic Energy Office, perhaps in coordination with other entities and agencies, coordinates a similar sort of fellow or effort to complement some of the efforts, you know, perhaps the USGS mapping effort that's that's going to be kicking off soon, or other things to really make sure we're bringing the attention to this subject here in Alaska. So just that is one thing that comes to mind as I listen to the talks here. I probably don't have to tell you this, but you know, the drivers for a hydrogen energy system are that hydrogen is the key to decarbonizing hard to decarbonize sectors of our global energy economy. And some of those major sectors are industry, electricity and heat production, agriculture, big consumers of hydrogen, whether it's to make, you know, fertilizer for agriculture or in various chemical processes. Anyhow, if we can produce, you know, hydrogen cleanly, or if it can be produced naturally, these are ways that we can decarbonize these huge energy consumptive sectors. This is they call it the H2 at scale diagram that the Department of Energy likes to put in all of its hydrogen publications. And it's a way of showing how hydrogen can advance affordable, you know, energy production and link all these different, maybe seemingly unrelated aspects of our energy system. So everything from power generation to transportation to gas infrastructure. And it takes a while to absorb. Maybe some of you have seen it before, but hydrogen really is one of those media that can unlock and also connect these different sectors, and really can be the key to moving us forward on our decarbonization pathway. This is just another way of looking at existing and emerging demands for hydrogen globally. Again, not just in, or not even in Alaska or the Arctic, but again, showing you the different sectors that could use hydrogen, whether it's, you know, made cleanly, made from natural gas, you know, produced naturally, et cetera. So again, transportation applications, chemicals and industry applications, power generations, integrated and hybrid energy systems. We have existing demands, and we also have emerging future demands. And you can see that it just hits so many different sectors and pieces of the energy ecosystem. My colleague Doug Wicks already talked about all the amazing research that ARPA-E is funding, so I won't spend much time on that. ARPA-E is our moonshot office. It's the office that funds these very emerging projects. Again, ARPA-E, you know, announced in 2023, you know, $20 million for these 18 projects across a variety of states, and it's about stimulation processes and management of extraction for hydrogen from geologic reservoirs. So again, I'm not going to go into the details there because you've already heard it, but I would be remiss in not mentioning this if in the context of the DOE's role in funding hydrogen or geologic hydrogen projects. Again, you've seen this diagram lots, or at least a couple times over the last yesterday and today. ARPA-E's geologic hydrogen highlights is again, as we heard, is about, you know, stimulated production, and it, you know, I think represents a paradigm shift in thinking about hydrogen as an energy source, and, you know, lowering the energy costs and increasing our national energy security and supply chain capabilities. And also, I should mention, you know, leveraging you know, expertise and resources from other industries such as geothermal, oil, gas, and mining. And I realize I've got leveraging typed twice there. Sorry, it'd be confusing. This is a graph or a cartoon that I made just thinking about how hydrogen could be used in Alaska. And again, not thinking about the type of hydrogen, but whether it's natural or even produced from renewable energy sources. But we start here with the steps in the hydrogen ecosystem at the top there. So production, going to delivery and storage, going to conversion, going to applications. And then below each of those, I have sort of some different options here. And for those of you who are from Alaska, I know you've probably already thought about these and heard about these, but for those of you who, you know, may not be from Alaska, it perhaps bears just a quick review. The production of hydrogen, as you know, could come from fossil fuel sources or non-fossil fuel sources or geologic sources. That's what we're talking about here. And that can produce hydrogen. And then there's also lots of conversations about converting those to carrier fuels, whether that's ammonia or methanol or other types of carriers. And then using those in fuel cells or combusting them directly or mixing them with other fuels. And they have the possibilities of being applied to a number of different energy sectors within our states. We are thinking about hydrogen for our remote communities. We have over 200 remote microgrid communities in Alaska, and communities are thinking about what they might do with excess renewables, how they might use hydrogen for seasonal energy needs. This is something that Paul is thinking about and trying to model, and he's having a ton of fun thinking about the complexities of what that might entail or be permittable or even not permittable. Hydrogen is being considered or thought about for the rail belt. The rail belt is our main electrical grid that runs from Fairbanks, where we are here, all the way down to Homer at the end of the Kenai Peninsula. It's our largest electrical grid in the state, but is still not connected to either Canada or the lower 48. Hydrogen could be blended with natural gas, and natural gas is the main energy source for both the heat and electricity on the rail belt. And we're facing a shortage of natural gas on the rail belt. And hydrogen, could be blended with natural gas to preserve the life of that natural gas. Perhaps it could even be used directly in some instances. There are also discussions in Alaska about exporting hydrogen, and I think there will be more conversations about that tomorrow in some of the panels, whether that's making hydrogen from natural gas combined with carbon capture to then export hydrogen to some of our Asian neighbors or other entities, as well as perhaps making it from other sources, from wind or other renewables or even hydroelectricity to then make a clean hydrogen that could be used in a variety of applications. So these are some of the opportunities that are being talked about in Alaska. None of them have borne fruit yet, but it is all summarized in an Alaska Hydrogen Opportunities Report, which is available publicly. If you Google it, you'll find it rather than trying to memorize that address. But this report came out of the Alaska Hydrogen Working Group, which I facilitate. We meet monthly, virtually. Our next meeting is next Tuesday, Election Day. And over about a year or two, we wrote this report, and it's not a roadmap, but it's a sort of a summary of the landscape and the opportunities for hydrogen integration into these different sectors in Alaska. Alaska has the potential to make progress in a number of the hydrogen ecosystem components, and both from our vast renewable energy potential, as well as our natural gas resources combined with carbon capture. There is definitely some discussion and consideration of seasonal energy storage opportunities, although there's complications and nuances associated with that. And I encourage you to go talk to Paul if you want more information. And then, of course, we're talking about storing hydrogen in depleted oil and gas reservoirs to enable affordable delivery of hydrogen at scale. And again, we'll hear more about that tomorrow. Bottom line, I think that we all realize, at least in the Hydrogen Working Group, is that near-term demonstrations will help pave the way. Once you prove the concept, people see, it can be done up here, and they follow. So that is something that the group is actively talking about. And I should mention this group is open to the public. So if you are interested, find me. Happy to invite you to our next meeting. It's 11:30 a.m., first Tuesday of the month. It's virtual. We generally have time for updates and connections, and then we also have a featured presentation. So let's see here. I just want to highlight a couple other DOE hydrogen programs and tools. beyond the ARPA-E funding. There are various programs, some of which are more well along than others. There's this H2 matchmaker to assist hydrogen suppliers and collaborators. There's the hydrogen shot, $1 per 1 kilogram in 1 decade, kicked off in 2021. So we've got until 2031 to figure that out. The Twin Cities initiative, where DOE helps pair up cities between US and elsewhere in the world to learn from each other. The H2 at scale is all about, again, what the name implies, scaling processes to make them economical. And then of course the hydrogen hubs, which were awarded, and some are doing better than others there, but it's definitely something that's trying to take off. I'll mention that Alaska did apply for one of those hubs and didn't get it. And that's one reason the hydrogen working group, I think, has really sort of coalesced and taken on more momentum and actually put out this report as well, is because I think the Alaska mindset about hydrogen and how it might be used is perhaps a little different than the rest of the United States. We're thinking about export, and I'm not sure any of the other hydrogen hubs are sort of framed that way. So some different circumstances up here, to be sure. I just end with ways to get in touch with the Arctic Energy Office. Again, we oversee a whole myriad selection of technologies, but we have a small group. This is some of us on top of Flat Top with Deputy Secretary Turk a year or two ago at the Sustainable Energy Conference at the end of May. It was still light at 10 p.m., so what else are you going to do except for go for a hike? We have a newsletter that comes out regularly. We are always happy to talk about projects. And the other thing we try to do in our office is be the portal to help folks navigate the Department of Energy with regard to Arctic concerns. So if you don't know which of the 60 offices to contact, you can get in touch with us and we can help you navigate who to talk to or who to set up meetings with to help figure out where to take your Arctic idea or project. So with that, thank you for your time, and I'll hand it over to our next presenter.
Whoa, 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 whoa. It's all good. Well, that woke me up. So I made the mistake of growing a beard during COVID, and coincidentally, my driver's license renewal came up in 2020. And so I have a license with me and a beard. And unfortunately, I have to fly not infrequently. And you'd be surprised how often I have to come up with some kind of, generally kind of like a little witty thing. Oh, what's going on? Oh, I'm not in witness protection anymore or whatever. But this is like a common recurring thing to the point that when I go through the security line, I have a little bit of trepidation just because I know I've got to have some level of banter about not having a beard anymore. Anyway, that's kind of an aside. Well, it's great to be here amongst all these learned doctors and scientists. It's, they brought me in to kind of help lower the IQ quotient of the room a little bit. I do love geologists, so it's really my privilege to lead DNR, which includes our division of geologic and geophysical surveys. In fact, our state geologist and director of the division, Melanie Worden, is here. But I love rocks, and I love jokes about rocks. For example, do you guys know why sedimentary rocks are so cheap? Because they're commonly on shale. Anyway, yeah, right? Isn't that a good, all right. The good thing is I am a lawyer. I don't have to make my living in stand-up, so we can pass on those opportunities. So I am the commissioner of the Department of Natural Resources, which means I don't know how to operate a show. And what does that mean exactly? Well, so it's really my responsibility to manage the state of Alaska's land and resources. So for all of you that are new to the state and visiting, first, welcome to the great state of Alaska. On behalf of Governor Mike Dunleavy, it's our privilege really to host you here in our beautiful Golden Heart City. As Lance mentioned, I started my career here in Fairbanks and was privileged to call myself a resident, and I really thoroughly enjoyed my time here in the interior. Alaska is unique amongst all of the other United States because when Alaska was acquired, first of all, it was an object of ridicule. It was former Secretary of State William Seward, who some of you may remember served in the Lincoln cabinet. It was really his initiative, his vision and foresight that led the United States into purchasing Alaska from the Russians. And some of you may know William Seward also, the same night that President Lincoln was assassinated, he also was the target of an assassination attempt, being in kind of the hierarchy of folks who could assume the presidency. His attacker, however, was foiled, but he used a knife and slashed the side of Secretary Seward's face, which is oftentimes when you see him portrayed in pictures, he's kind of faces off to one side. He kind of hides the side of his face that was wounded in the knife attack. But people called the purchase of Alaska Seward's folly. You know, they thought it was a frozen wasteland. Even, you know, up into the 1890s, a lot of people questioned what a terrible deal it was for the U.S. to purchase Alaska for what, 2.5 cents an acre, I think was the going rate. But Seward had a vision. And of course, in the 1890s, the discovery of gold in the Klondike and the great influx of prospectors to the northern regions started to change that perspective. And from the Klondike, folks fanned out. Felix Pedro down here in the Tanana Valley ends up finding a little bit of gold, and so on and so forth. You start seeing people trekking north in search of resources. And that was a common theme throughout much of the state's early history as a U.S. territory. And so as we had prospectors, we had loggers, we had commercial fishing interests, and so on and so forth. And a lot of those folks, you know, they came up, they made their fortune, or maybe they didn't. They extracted their resources and they left. They went back to Washington or Oregon. They went back to the rest of the lower 48. And Alaska really didn't have much to show for it. And so in the 1950s, late 1950s, when there was a lot of debate and discussion around Alaska's statehood, it was really understood that in order for Alaska to be self-sufficient, in order for us to not be a perpetual ward on the federal government, that ownership of land, and particularly ownership of resources, needed to be vested in the state. That is, the state needed to be free to develop its own lands and its own resources in order to provide for its people. And so, as you see on this land status map, the state of Alaska manages and owns a significant portion of the state's land base. So Alaska has roughly 365 million acres. Of that, 100 million acres are currently managed by the state. Of uplands, we also manage another 65 million acres of tidelands, with the remainder of lands being in the state generally being held by the federal government, and then a smaller percentage being held in private hands, including our Alaska Native corporations. So as the DNR commissioner, it's my job to oversee the management of these lands consistent with Article 8 of our state's constitution, which Lance cited in the intro, which means that we're very interested in the resources that lie under our lands, because not only do these resources provide all kinds of new and interesting opportunities, but fundamentally resource development in Alaska translates directly to benefiting human lives. As we drill new oil wells, as we produce more gas, as we mine more gold or any other kind of mineral, as we fell more trees, those revenues that derive from myriad taxes and fees and so on and so forth go into the state's general fund treasury. Or they also go into the state's permanent fund, which has a value of roughly $80 billion. It's one of the largest, certainly the largest sovereign wealth fund held by a United State, and is one of the larger ones in the world. But those monies, those resources directly translate to services for Alaskan, for roads, for police, for fire, for education, so on and so forth. So for us, managing resources is fundamentally about improving people's lives. In fact, my spiel as commissioner to my people right now is we have an initiative. It's called DNR 2033. It's about how do we look at what the state is going to look at in the next 10 years. And one of the things that I try to instill in the people that work at DNR is that by virtue of working at DNR, which I would argue is the most important state agency in the state of Alaska, you have the ability to shape the future of Alaska unlike anyone else. You know, somebody could go to work at the Department of Revenue, the Department of Administration, you know, they clock in at 8:30, maybe they take an hour and 20 minutes for lunch, they clock out at 4. You know, I mean, they do some work and you know, it's useful in some form or fashion. But at DNR, yeah, that's fine. At DNR, we're making decisions on the management of our state's lands and resources. And because of that, in our hands really lies the future of the state. How we manage our lands, how we manage our resources, the approaches that we take really will have a significant impact on the trajectory of our state. And so the slogan is, you know, we can transform the future of Alaska today at DNR. And really that's what that message is all about, which I think really ties in well with this conference talking about geologic hydrogen, because again, it's another very exciting potential resource that, that we have, or that we potentially have here in the state, that again could make a big difference in shaping the future trajectory of the state. You know, similar to Richard's comments, I think we're starting now to take a look at the statutory framework that we have that would govern potential geologic hydrogen production. I think similar to the federal statutes, there's some ambiguity as to, yeah, I mean, hydrogen's not really a hydrocarbon, you know, does that really kind of fit in with our existing oil and gas leasing structure? You know, arguably, we could probably say that we do have that authority and that we could manage this. I mean, what is clear is that the state has that unified management of our land, so we own both the surface and the subsurface, which is another great, I think, benefit to potential developers here in the state. You don't have to worry about going and negotiating with maybe a federal landowner or some adjacent private landowners or some rancher or farmer or somebody else that has some land holding that's going to complicate what you might be looking for at a development project. Chances are you can come to the state of Alaska and we're going to have that one-stop shop. We're going to be the managers of the surface estate. We're going to be the owners of the subsurface estate. And that level of continuity will help facilitate, I think, the leasing and predictability element to working with the state of Alaska in these initiatives. But fundamentally, we are going to take a look at what, you know, whether it merits statutory changes to just ensure that our authority in this area is clear. We're actually looking at it currently in regards to helium, which similar to the federal government, the state kind of withdrew helium from our general oil and gas leases, but we have areas in the state that have some potentially significant helium potential. And so for us, ensuring that we've got, again, the right regulatory framework in place that can manage that will also be important in the context of hydrogen. I'll also say some other related initiatives that we've looked at as a state that I think are germane and relevant to, as we see this hydrogen market develop, is this last session, we passed legislation called HB 50, which legalized or created a framework for carbon capture, utilization, and storage. And this is a very exciting initiative for us. Alaska has great rocks, right? A lot of you that have spent your lives up here looking at what we've got to offer, I think, would acknowledge that. We know and we believe that we have significant CO2 sequestration potential. Some estimates are up to 50 gigatons in some of our basins. And so we are very interested in pursuing opportunities with industry, with other nations, other entities that are interested in looking at Alaska's carbon capture, utilization, and storage potential. Just a couple of weeks ago, Sumitomo Corporation, which is a major Japanese industrial conglomerate, announced that they are entering into a partnership with Hillcorp, which is one of our big oil and gas operators across the state, specifically to look at carbon capture, utilization, and storage efforts in the Cook Inlet. We've also met with other companies and entities, which I can't name, that are similarly looking to understand more about what Alaska has, and who are really on the forefront of developing a lot of the ships and the equipment and methodology necessary to both capture carbon, put it into ship, haul it from Asia, and then sequestering it here in Alaska. But because of the legislature's approval of HB 50, my office is currently embarked in the regulatory process of promulgating the rules around carbon capture, utilization, and storage. And I believe we are currently in the public comment period on that right now, and certainly would, for any entities or parties that are interested in taking a look at that, I encourage you to take a look at our regs and certainly provide feedback, because we like to make this as robust as we possibly can. In addition, we have various partnerships, certainly supportive of the university and their efforts in doing some of the CCUS delineation and characterization work to better understand what the potential is in the Cook Inlet, in particular right now for carbon capture potential. But some of those learnings and data could also likely inform what we might have available for hydrogen storage as well. So on the hydrogen front, I know you guys have been talking kind of geological hydrogen ad nauseum. I mean, that's the real crux of this. The other thing that we're seeing on a statewide level is we've had a number of entities that are very interested in looking to Alaska as a hydrogen manufacturing hub. Most of these entities are really looking at building out large-scale renewable projects, generally windmill driven, that would generate gigawatts worth of energy that they would then convert over into hydrogen production. Part of this is because, one, Alaska has a massive land base, and there's not a lot of areas in the lower 48 where you can build some of these types of wind farms to scale to generate that much energy. And not run into myriad other issues. So they're also looking at Alaska because, as many of you know, we sit on a geopolitically strategic part on the globe. Alaska is closer to Asia than, of course, any other West Coast port. Alaska also has had long-term relationships with Asia. We were the first state in which LNG was exported to Japan. I guess I'm looking at Meade and his history back in the 1960s, 69. So we had that long history of LNG exports, building that relationship with Japan, being a reliable provider of energy for them. So for Alaska to become a hydrogen hub potentially, and starting to manufacture, produce both hydrogen and those derivative products that Aaron and Richard talked about, whether that's ammonia, whether that's e-fuels, whatever it might be, our position on the globe, being close to Asia along the Great Circle shipping route, the fact that we have these long-standing relationships, the fact that our shipping routes don't have to pass through contested areas, like the South China Sea or the Straits of Malacca, or wherever around the Horn of Africa. We've got some real advantages to play a role in kind of global energy security and stability, particularly for our Asian allies. And so at the state of Alaska, we're very focused on trying to take advantage of that fact and building on those long-term relationships with countries like Japan, like Korea, to see this new energy renaissance really take place. And I think I have one more slide. Oh, yes. So, you know, again, the big area in terms of where we can contribute to geologic hydrogen is really with Melanie and her team. They are the learned scholars and doctors of DNR. They, you know, really the fundamental role that we play at DNR and DGGS is they're the ones out doing that characterization and delineation work. They're the ones going out and collecting the data and helping to de-risk for those companies or entities that are willing to actually then go out and do that more robust exploration, helping them see, you know, where it is that we have potential, where we have the right kinds of source rocks, you know, the types of places where you want to try to site your drill bits and set up your camp and do all that sort of thing. So I think I'll just kind of pause there because we want to get into the discussion, but really we're, from a state perspective, we're very excited about the potential of geologic hydrogen as we are about developing all of our energy sources. I'll have to talk to Richard about geothermal because that's another big initiative of the state to, we're on the ring of fire and you know, we even have a volcano right now that's been raised to a yellow level of awareness that I'm kind of keen to see if it'll go off because I just have I love volcanoes, so I'm just kind of intrigued by it, which is kind of macabre. But I live right across the inlet from it, so I could really just have a great show if it lets go. But we've got geothermal potential because of that strategic location, again, being in the ring of fire and having myriad systems, including here in the interior, we have decomposing radioactive granites and all that sort of thing that somehow heat up rocks and do all that kind of stuff. So anyways, great to see you guys and looking forward to the discussion.
Thank you. Big round of applause for everybody. Yeah, but they'll be online. I think we're going to have to actually tie up here pretty quick. I know. And John, do you know why the volcano spews?
What's that?
I don't know. Just trying to figure out more jokes, but no, I don't think we have time, correct, for more questions, or do we have? We're off at a couple. When we're off at 2:15 or 2:30, 2:15, 3:15. Yeah, I know. Come on, okay. If we questions. But I did want to say, you know, the ecosystem thing, I think we had that exercise earlier. Are people coordinating? Aaron showed, you know, that's building that ecosystem. Also, brain drain didn't come up. It comes up a lot. Aaron's an example of somebody who came back. It took 20 years. And Richard, I think it's pretty neat that we're involved with something that's not even defined as a gas, mineral, or energy resource. So there's an opportunity there. And John, absolutely, DNR is the best agency. So
yes, we are.
Are you bringing up the questions or just shout out? Yes. Go ahead.
Yeah, my question is, first off, if it's not hydrocarbon, it's a mineral, right? So we can still go out and prospect for minerals under your law, under your legal regime. But you got to keep AOGCC out of it because when somebody was prospecting for geothermal, decided to run it like regulated like an oil well and messed up the drilling.
Good comment. Sure.
Okay, we can go after it. Yep. Yep.
Well, that actually doesn't work for us because jurisdiction over gas minerals is consistently mentioned but never defined as a statute. However, BLM has defined the word gas broadly to likely include hydrogen under its current rule. In addition, 43 CFR 3170.3, subparagraph A, and Watt versus Western Nuclear Incorporated interprets the word mineral suggests H2 is a mineral. So you'll have to see. So maybe.
So with that, if for the panelists, there's some questions on up there if anybody would like to grab one or two of those. I knew there'd be an answer. Thank you for the love it. That is awesome. Okay, here you go, panelists. Address any of those.
Adding subsurface stored simulated and natural hydrogen to the H2 at scale diagram. You know what? I'll take that back to Sunita at the Hydrogen Fuel Cells and Technology Office. Appreciate it.
Yeah, those are the other ones.
I had a comment, Richard, that the RFI was super onerous or onerous, however you say that word. So there are exactly 2 companies in the world that are financially capitalized and therefore have people to work on it, and the rest of it's a startup game. And so the extreme amount of information asked for in the RFI was so burdensome for many startups that I spoke with. I'm at Stanford, but leaving Stanford to work in natural hydrogen, it was so burdensome for startups to even contemplate responding to. Many of the startups I spoke to couldn't even begin to approach it. So I want to just give you that feedback in a very polite, kind way.
Well, I'll take that as a polite, kind way. Yeah, the RFI actually is pretty short, and from an RFI perspective, I think it was like 2 or 3 pages long. Are you talking about the one for the Defense Energy Consortium, which? Well, I had 2 that went out. So for this particular one here, though, I've received before the date, we've received over 20 responses to it that are there. Some of them are actually from the States. I've received it from various places. But the reason, so in that particular RFI, it wasn't focused so much on the technical perspective. It was focused on more of these other issues that are there. So yeah, I'm sorry to hear that, but those are questions that we need to know to create an RFP that's going to benefit us. So I'll give you an example of how RFPs don't work well with us, is that if someone responds to it and if we don't do our good due diligence, so you're talking about with startups. So we do look at, I look at performas on those. When we look at them, I look at the cap tables. I want to know who owns the companies. I want to look at their financials to see what's going on. So, so for that particular RFI, it was not focused on the technical aspects, focused on others. But we'd like you to respond. You didn't have to respond, by the way, for everyone that's out there. Let's say there's 20 questions. I can't remember what it was. There are probably that many. If you can respond to 2 or 3 that you think are okay, that's going to help us inform the RFP. So I don't discourage you from seeing something that might be a little onerous and maybe difficult to respond to, but appreciate the feedback.
I think we have time for probably one more, right? One more. Go ahead. You got the mic.
Yeah. Richard, you mentioned that you were the Air Force is interested in resilient energy sources as opposed to, green energy sources, for example. How do you, in the context of hydrogen, blue hydrogen, green hydrogen, gold hydrogen, how do you define resilient? Is it sort of defensible?
So for us, resilience is not dependent whether it's, what the energy source is. Energy resilience for us is ensuring that we can complete our military mission 24/7, 365. So right now, we complete that now with fossil fuels, but our office also has mandates from the executive department to meet our, energy, goals for the 2030 to reduce, to become more carbon free. We will not mention, climate and things of that nature because due to the political sensitivities towards it. So our first emphasis will always be resilience. Like I mentioned, I believe that we can get to the energy resilience and utilize new technologies that can get us and create a sustainable planet. So you're hearing that from me, but you won't see that in any publications due to political sensitivity. So the answer to your question would be anything. It could be nuclear, it could be geothermal we're looking at. So most of those are clean energy resources. The long duration energy storage is important for us because a lot of sustainable or energies that are out there like wind and solar, most people didn't think about the fact with the intermittency, they didn't think about, we need backup energy generation for that. So to answer your question, resilience to us is ensuring that we can meet our military mission. If we have a clean energy response to that, to the energy demand, we're very open to that, and we're pushing those efforts, like with those ones that I mentioned to you. I don't know if to answer your question, but we can talk afterwards.
Thanks. All right, another round of applause. And again, thank you for the answer. Why did the volcano erupt? For lava. That's a takeaway. For the lava.
Thank you. So what we're going to move on to is the summary discussion, and we're going to do it like a fishbowl, like we did yesterday. Mark's going to moderate. The question is, regarding geologic research in Alaska between now and 2030, what would progress look like?
Hey guys, you got a little more energy left in you? One more exercise? I think this will be fun. So envision what you think a research program, what can we have in place and know by 2030 in Alaska if everything goes right. We talked about what we could do in 5 years, but let's stretch that out to 2030. 2030 is the point where we're supposed to make these significant climate carbon goals, right? Huge carbon goals by 2030, and then on by 2050 to 80% reduction, right? So 2030 is sort of a big COP goal. I mean, we're doing geological hydrogen for not just carbon mitigation, but for energy as well for Alaskans. So if we think about the economic benefits of it, we think about the challenges of getting solid progress. What do you think we can do by 2030? What will the landscape look like? What science questions can we answer? What kind of licensing program? Could we have active exploration? Would there be any discoveries by then? So you have to vision out in all programs, right? What's going to be our end result, kind of our midterm results. So by 2030, we'll have the USGS assessment, and maybe the second version of it by then, possibly a refined version. We'll have had some more additional active research. We'll have acquired more data. So think about 7 years from now, we're having this conference. What have we learned? And where are we with respect to exploration or development? So I'd like volunteers to come up here and tell us what you think, what you can envision. Anybody, any takers? Come on up, please. Thank you. Yeah, really, what can we accomplish by 2030 with respect to research and exploration and even development, if you think it can get that far? You sit down. The rule is you sit down.
Well, the bottom line is that I didn't realize how big my ignorance was about this topic. But when I think about what's feasible, what struck me the most is the hydrologic talk that Alexis gave and the sampling that can be done and surveying the state hydrologically. I don't think there's been, unless I'm mistaken, anything systematic in Alaska about this. But if you're looking for something that's feasible to build on the research that is part of this, that is one place that I would look at. And when I say hydrologically, I mean the biomass sampling that would be done in whatever samples that you would be taking. I think it's, I looked at her chart of that nonlinear growth rate and thought, you get a sample of a bunch of biomass that's anomalously very, very high. You do a gradient map of your flow streams in the subsurface, and you get a potential way to reverse engineer where these plumes of anomalously high biomass are in the water, and you potentially have chimneys of hydrogen indirectly indicated. To me, that seems like a low-hanging fruit, relatively inexpensive thing to do. The boring and the drilling for sampling on that should be, again, relatively inexpensive. That's the idea I have.
Thanks. I think that the first step is this prospectivity mapping that we're doing based on the geology that we know and what needs to come together to have conducive settings for accumulations of natural hydrogen. And so that's ongoing, and we'll have the first maps coming out soon. And then, as Mark said, it's going to be a a continuous process of refining both our models and also the input data. But I think that a critical next step is once we've identified these key areas that have the highest prospectivity, then we need to get out on the ground and look for evidence that we actually have an active hydrogen system. Just like with petroleum systems, people look for petroleum seeps, and so as a validation for an active petroleum system, so we need to go out and validate that there's an active hydrogen system in some areas, and then once those have been identified, then we need to do much more detailed, high-resolution subsurface characterization. So getting out there and doing the geophysics and hopefully, I mean, there are some existing geophysical data sets that we can leverage, but I think that we're going to need to collect new high-resolution, really high-quality data that we can then use to identify subsurface targets that will be of high value. And then ultimately, we're going to need to drill. We're going to need to drill a lot of wells. I think that there's going to be a lot of failures, a lot of false starts, but we will need to drill wells, but we're going to learn a lot from every well we drill, I think. So, and it's going to take a concerted effort. This is not something USGS can do on its own or the University of Alaska. It's got to be a consortium of university and state and federal support and everything. So that's my high level overview of where I think we can go. And we can do this in 5 to 7 years and make a lot of progress, really learn a lot. And Alaska is really an ideal place to do this kind of work. So I hope we can get the players all together to make this move forward.
Thanks. Simon Harrison. I used to be a business developer in the international oil and gas business. And so I just wanted to emphasize my support for a couple of these points here, because I think they're great points. They weren't my points, but they're great points. And I think the top one, point 25, excellent. Point 17, basically, I think the state of Alaska can't really afford or probably doesn't want to and probably can't afford to invest its own money in hydrogen exploration. But it can create the market conditions and land access conditions to make that happen. I used to teach a course on running an oil company, and the throwaway line was, to be successful, all you had to do was get land and drill wells. And that was it. More land and the more wells you drill, the better. And I think the state of Alaska should be aiming not to invest in exploration, but to create a queue of investors that line up around the block where the DNR's offices are, because the state of Alaska has offered attractive fiscal and regulatory terms that are better than anywhere else in the world to look for and develop hydrogen, natural hydrogen. And that will light a fire under hydrogen exploration in Alaska. Thank you.
Thanks, Mark. A couple of things for the non-Alaskans here. We have tried a couple of times to induce more gas drilling in Cook Inlet. We were in the early 2010 timeframe. We were forecasting brownouts. We put a tax credit, essentially a transferable tax credit on oil drilling, and what do we run up about a $700 million bill for North Slope and that the governor didn't want to pay for a while. The next governor didn't want to pay for a while, but we did get through the Cook Inlet, the first Cook Inlet thing. We're now having a second situation, and we don't want to do the direct subsidy on the tax credit. So I'm just kind of concerned, Mark, that we get into some sort of scheme here recommending out of here that the state by a lot of drilling as that. And I'm not sure there's a tax credit. I'm not sure there's a royalty forgiveness, and I'm not sure there's any particular state handle except maybe access to land that is going to produce this. But the main thing is this: it reminds me of a trip I led with a group of geothermal experts from your old agency, Mark, to Iceland in the early 2010s. And we said, well, okay, how are we going to get geothermal going? And they said, well, how much money do you have to subsidize this? And we said, what do you mean subsidize this? You're running your power off this, 25% of your power, 80% of your power and heat comes off geothermal. What's the problem? They said, no. We had to figure out we had more dry holes. We had to drill dozens of different ways, dozens of different times before we ever got kind of an economic scenario that worked. And that's what I've heard described here. And it seems to me you've got essentially two general scenarios right now. One is stimulated rock, look, and the other is reservoirs. And you've got some data, but we got to start with the data. And you've got DGGS guys who said today that they haven't looked at well logs yet. So let's figure out kind of a massive research program to figure out what is the best areas to try it. And then the next thing is that if it comes to that kind of drilling, we had, I think, $18 million of DOE money for a ground source geothermal project that actually didn't go through because of an AOGCC problem that I mentioned before. But I think we can prove that maybe we're better than Kansas, maybe we're not better than Kansas, but we ought to be drilling here and in Kansas and in any other place that it makes sense to try to figure out what geology is reliable on this. And the only other thing I would say is that right now the hydrogen sources in Alaska are huge. Simon, who just spoke, is working with David on a wind hydrogen project, if I'm not mistaken. There are several others that John Boyle mentioned that are being talked about. The decarbonization of natural gas technologies are changing rapidly, and I'll talk about that tomorrow. And it's not because I favor one over another. It's that we got to start generating a market for hydrogen. Okay, there's not a clear one. I mean, I was joking. Smucker's brings out pre-made peanut butter and jelly sandwiches because they look at our market and our mothers made it all for us, for generations. I mean, the fact is, if we start using hydrogen where it makes sense to use it, and it won't always make sense to use it every place that Aaron's chart has, but it'll make sense to use it more and more. That's going to generate the demand. But I would say a government assessment across the governments, and it was really good to see the U.S. and Canada working together today. I would say bring in the state logs, bring in the other logs, figure that out, as well as think about it as a mining project as well as a drilling project. Good luck.
Other folks want to hazard a guess of, let's simplify it a little bit. What do you think we will have learned in Alaska by 2030, and regardless of whether or not we have commercial production or not, and taking into account what the rest of the world is doing? I mean, we're not doing this in isolation. That's one of the major important messages of this today. There is a lot of drilling going on now. There are more companies. We're learning at an incredible rate right now. And so take me 5 years, 6 years from now, what do you think we've learned that's applicable to Alaska? And the second question is, how much of that can be applied to Alaska or will be applied to Alaska? So any takers? Great.
So this is another observation which I get from projecting from the oil and gas business, is that Alaska might have huge quantities of hydrogen, Probably does. It also has huge quantities of methane gas on the North Slope, which it has failed to sell for 40 years at $1 a unit. So the problem Alaska has, even if it has hydrogen, is that it has such a small population and such a small economy that it has an inadequate, probably has an inadequate demand for hydrogen. And that just like for North Slope natural gas, for copper in the Copper Valley, Kennecott Mine, for excess gas in the Cook Inlet that was exported as ammonia and LNG for a decade or so, that essentially if you find commercial quantities, which are large quantities of a resource in Alaska, because of the absence of a market, you need to export it. And so which comes first, the chicken or the egg? Do you find that large resource and then find a way to export it, or do you find a market which leads you to look for the large resource? That I can't answer, but I caution you against thinking that just converting all the trucks that run around Anchorage to run on hydrogen is going to move the needle in terms of looking for large quantities of hydrogen. That is probably a market that is an order of magnitude or even too small. I don't have a solution.
Just a couple of thoughts. I mean, I think in a few years from now, we'll have a lot more data, which is what's needed right now. Where people are really trying to measure and detect hydrogen and can scale that resource and hopefully have done some level of production in a target site. And that will really help to focus what could be. What's been interesting, though, is when you were just talking about, or when we were just hearing about the commercialization, what it would take to scale, might have to export. And so it depends what the dreams are that Alaska has in terms of its economic impact. On an energy impact, one of the most exciting sort of conversations here to me have been more what can be done at a local level for energy production. I just think it's really exciting to think about what these remote communities could do if hydrogen was an available resource. And maybe Alaska should start smaller and not try to shoot the moon yet, but figure out how to impact local communities and make it be beneficial to them, and then look at whether or not there's also ways to grow the market. So that's just something I feel like I've learned here so far.
So what we've seen is two competing models for energy development. One follows the big export model after the oil embargo that got Alaska on the map. Wouldn't have happened without a international crisis. The second model is a more sustainable internal energy production model. And so we can look at the two models, the Saudi Arabia model, or we can look at the Iceland model, where Iceland is integrating their energy infrastructure, bringing smelters in, but primarily serving their internal markets. We learned that their data set is both at the same time. They're getting data centers that come there. So as we look at the paradigm shifts, I think hydrogen is a paradigm shift in how energy is not only produced, but used. And that's one of the thought process exercises we have to go through. How real is that paradigm shift? How much effort's going to be made to decarbonize, both within the oil industry and with global energy sources, and what premium will it be or what penalty will be for not doing that? That's built into the structure. We don't know. So that's a different piece of energy economics than we faced. Another example of that is, are we going to build out infrastructure in Alaska rather than export? We have an export economy, a commodity export economy. Are we going to diversify the Alaskan economy by building more capacity to build value added internally with the state? Maybe that starts with mining and maybe doing mine development and mine processing in Alaska. Maybe that starts with making our own jet fuel, as some have proposed here. Maybe that starts with making our own ship fuel, et cetera, right? So incrementally, these are big economic questions for us. What is the economic future that Alaskans want to chart? At the same time, if we don't do the research, I would argue, we can't even ask the question, right? We don't have the capacity to do this with clean energy, because we can do some with renewables, but that's going to be deferred to some degree until we have enough renewables to meet the basic internal needs of the state. So I think 7 years is a good time period, because that takes us to the crisis in Cook Inlet. It takes us to deal with the issue of the technology and the approaches that are going to be learned elsewhere externally, and gives us some time internally to do the research pieces of this. I would say one other thing. Alaska now has no geological hydrogen research program whatsoever. That's the reason for this workshop, is how do we develop one? If we don't make the effort to do that, it'll never happen. So how much is it worth to the state to do this? How much is it worth to the federal government to do this? How much can we export? And the other thing, I think, in my mind, when I looked at the energy transition, we have a huge challenge with respect to what is that oil and gas market going to be 30 years from now? If we're dependent on that for an economy, maybe there won't be a lot of export by that point. That world will convert. The world needs to convert. So as we see that change, what's the value of our main export commodity out there? I mean, I think of the time when my ancestors lived in Texas, and they invested in horses because they didn't think cars were going to work. So there is exhaustive examples of that, right? We're going to go for kerosene, or kerosene created from plants, or where we're going to go with oil and gas. Big decisions were made of how to do lamp oil, in that time frame. And oil and gas won, and then it took off extremely well with transportation. So when you see niche markets, you can see these switches. I would argue electricity simply will never do the industrial process as well. So if Alaska wants to do industrial processes, it's going to need alternative fuels in the future. So as we look at this thing strategically, what are those fundamental questions of the future of the state? And I think you all brought up excellent points about the challenges of scale, but fundamentally, what is the vision for the future for the state? And how are we going to understand the changes externally that are affecting us are really big questions. So if we can't somewhat make a case, in my opinion, on hydrogen, we won't get the research funding up here and the emphasis, because there are always critical minerals. There's always another issue and an immense budget that's going to need for climate adaptation up here. We know how many villages we have to move. We know the infrastructure we have to build, and we'll make the decisions on how we're going to do Cook Inlet without much hydrogen, unless, again, we do electrolysis or steam reforming at large scale. And not saying we shouldn't, but we see the cost challenges with that. And I think we'll see from Doug Wicks tomorrow those potential cost differentials. So I'm talking too much. I'd love someone else to come up here while I'm filibustering. Any other ideas? I will say, I believe, I'll give you my version. I believe that we will form a consortium that will do the research. That consortium will fill in these gaps of existing data. We will have some analysis. We'll have some discovery of hydrogen seeps if we really start looking for them. We may even get enough experimental work, geophysics, to verify the subsurface, and the USGS maps will help a lot with that. And we'll have targeted ability to drill wells. And I would hope, my vision, we would have a regulatory structure that would allow us to drill, and it would allow for private infrastructure to come in. If we're at that point, if we're sort of shovel ready for exploration, then we can see who comes, and we can see what opportunities there are. And I think in that point, if we are as good as if the data suggests today, we will get some investment. We got oil and gas investment from the 1940s on up here, real high risk wells, most of which didn't pay off until Prudhoe Bay, except for Cook Inlet. But you think it was was it the 8th or the 9th well at Prudhoe in the program that discovered Prudhoe Bay? It was not a prime prospect. They were after the Nanushuk play, ironically the play that's being developed now. But the story is, it's going to take a lot of wells, as Jeff said. It's going to take time. But if we don't do this fundamental baseline research, we will not be drillable. If we don't have a regulatory structure that allows for it and a licensing program, it won't move forward. So to me, if that infrastructure is in place by 2030, we're highly successful. And, you know, if you build it, maybe they'll come. And I think it's highly likely, actually, we will see it, because if you look at the potential for minerals development, in particular, energy sources from mines in these basins is an absolute critical thing. Communities need energy for transportation and for heating. And so, you know, electricity is okay, but it isn't great for those properties. And if you look at PCE, and it's controversial, but look how much we have to subsidize energy in this state to keep the state viable. If they had energy sources rather than subsidy, maybe it'd be a better deal for it. It'd certainly be better environmentally. So we have a lot of choices out here. And I guess it's not for us, it's for the policymakers to make those choices. But I think without the research, that these choices will be off the table with hydrogen. So anyway, anyone else want to talk? Again, my filibuster's almost over. Barb, you want to close this out?
What I have to say has a little bit to do with this last section. If I came up here and sat, maybe I'll just sit here and I'll be the closing part. When people start a new initiative, we often look at the ARPA-Es of the world. We look at the DOE, we look at labs, we look at universities, we look at institutions and organizations to invest in things. But in fact, there is a crucial 15% of any initiative that cannot be done by organizations and must be done and is done by individuals doing tiny actions. So we call that the crucial 15%. So it might be, I live in Kansas and I personally know my senator and I ask my senator to vote for a certain bill. Or I write a letter, or who knows what it is for this. But we all have resources that we can put to this. We have resources and we have our own authority. So if you will look in your boxes, there's a sheet that says 15% solutions. And this section is because we've been looking at what can we do to further research? Well, what can we individually do? Can someone hand me one? Yeah, they're under the boxes, sorry. Thank you. I should have brought one up. So the question is, what is your 15%? What can you do? What do you have discretion to do? What do you have freedom to do? What can you do without any more resources or authority? Who can you contact? What next step can you do yourself? So that just fill out this form and then think about who and what can help you if you need a little bit of extra help. But think primarily about what you yourself can do. And we'll do this we'll spend 5 minutes filling out the form, and then I'll tell you the next step. Sounds like many of you are done now. You can continue filling this sheet out later if you'd like. Here's what we're going to do now. I have a few announcements. I'm going to do the announcements first before people leave. One is that we would really like you to clean up your personal trash off the table. So if you have pop cans or, you know, chip bags or whatever, take them with you. Do leave the things that we've been writing on today, so that we can pick them up and use them. Bring this sheet that you're filling out now back tomorrow. We're not done yet, but I'm just doing this announcements. We also would like you to fill out a feedback form. There are those half sheets. It's the same as yesterday's form. We'll have a different form tomorrow. We appreciate the feedback. I get the feedback about this last thing, the crowdsourcing thing we did in the back is a little chaotic. I understand that, but think about the other things. What worked, what didn't work. And now, what we're going to do with these 15% solutions is find somebody, or one person, share your ideas and give each other more ideas about how you could implement your 15%. Find a buddy and do that. And when you're done doing that, and you're done with your feedback form, then you're free to go. No, I just did it essentially. Why? Okay. Okay, you want to say something?
Yeah. So one more thing before you guys go. I have up here a sample of an output from a symposium specifically on permafrost and infrastructure that happened here at UAF, and it was in conjunction with NSF and UIC Science. It's very interesting if you're interested in permafrost at all, or in the infrastructure work that we've been doing here at UAF, and I can get you a copy of this. So and I could also mail it to you. You don't have to carry it. I understand about travel. I'm going to have this sign up and this as a sample over at the table. And Elena is going to hold her hand up. Elena is going to help us gather names and addresses. I'm also going to say, very subtle, Steve, it's really cool to have these kind of outputs from these kind of meetings. Super subtle.
We're a little bit of disorder.
Okay, that's fine. Yes. Well, you said you weren't going to.
Okay, I got the message.
So you did an announcement. All right, please stay, do your 15% solutions discussion, your feedback form, put the feedback form on the table, and then you're free to go.